Ini peserta nggak ada aturan penanaan? Nggak perlu berapa nanti?
Nanti ya. Suruh hari ini.
Oh, ada tinggalnya.
Oh, ada nama-nama. Ada angka-angka.
Oh, itu.
Angka. Oh, iya iya iya.
Yang lain sudah ngirim semua?
Sudah tadi
Oke,
sampai.
oh ya. Kan saya tuh.
Iya.
Itu loh, di map itu loh Pak, di map. Soundmu dicek ya, kira. Soundmu dicek loh.
Tes.
Maksudnya paketnya
Sudah dikeluarkan ya undangan.
Tulisannya ini loh kok hilang. Apa pas di download sudah hilang?
kata beri PDF.
Oh gitu. Orang nggak hilang. Oh udah. Terus ini simpan di mana?
Nanti saya kopikan.
Oh ya wes. Nah, oh tak sign up saya.
Ya. Bintang 1 Pak Arjono kon siap-siap. Pak Faru
Nurule.
Oh, Mbak Nurul. Durung.
Ladies and gentlemen, the conference will begin shortly. Please have a nice seat and make sure to mute your microphone. Good morning, ladies and gentlemen. First of all, I'd like to introduce myself. My name is Shafira Hairunisa, and I'll be the master of ceremony for today's conference. We are delighted to welcome you to the 10th International Conference on Physics and its Applications, Icopia 2020. Icopia is a biannual conference dedicated to promote recent innovations and share knowledge in physics and its applications. It aims to foster international scientific networking and cooperation. It also aims to bring together researchers, academicians, and scholars around the world to share their research. This event is also a potential to have the collaboration among researchers. The Honorable Professor Ahmad Yunus, as Vice Rector of Academic Affairs, Universitas 11 Maret. The Honorable Dr. Nuryani, as Chairman of the 10th International Conference on Physics and its Applications, Icopia 2020. And to the Honorable, our keynote speakers, Professor Khairul bin Ahmad from University Tun Hussein on Malaysia, Dr. Steve Ling from the Center for Health Technologies, University of Technology, Sydney, Professor Budi Purnama from Universitas 11 Maret, Indonesia, Professor Didier Pascal from Université du Lidogal, Côte d'Ivoire, France. And also we welcome all the presenters and participants of Icopia 2020. Before we continue to the conference, we will listen to Indonesian national anthem, Indonesia Raya. Please have a nice seat. Thank you. Ladies and gentlemen, we are now going to listen to the welcoming speech by the chairman of Icopia 2020. Please welcome Dr. Nuryani.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Honorable Vice Rector, Universitas 11 Maret, Professor Ahmad Yunus. Honorable Dean of the Faculty of Mathematics and Sciences, Dr. Harjana. And Honorable keynote speaker today, Professor Muhammad Khairuddin Ahmad from UTHO Malaysia, and Honorable Professor Didier Fasquel from France. I think Professor Didier is not yet joined this conference because in the front is still early morning. And Honorable Dr. Stifling from University of Technology, Sydney, Australia. And also Honorable our keynote speaker, Professor Putih Purnama from Universitas 11 Maret. Ladies and gentlemen, on behalf of the Icopia organizer, I would like to extend my warm welcome you all to the 10th Icopia conference. Also, I would like to extend a special welcome to our international speakers today from France, from Malaysia, and also from Australia, and also from my university. First of all, that Icopia is a biannual conference organized by Physics Department, Universitas 11 Maret. And the author of this conference, this paper of this conference is from Indonesia and also from overseas. As we know that this year Icopia is already in the 10th one, and so already many articles, many papers already published by Icopia this year, and also the before this year, that the 8th and 9th Icopia, the papers is published by the Journal of Physics Conference Series. And also this year, the article will be published by IOP, Journal of Physics Conference Series. Ladies and gentlemen, this year is special, different with the previous one of the Icopia before, because this year is in the pandemic COVID situation. So Icopia this year is conducted online using Zoom, and I apologize about this thing, and I think you already know about this. The Icopia before this already offline, so actually you can enjoy the solo, but today is special because the conference is conducted offline. Ladies and gentlemen, about 100 papers or article will be presented in this year. This including from Indonesia and also from overseas. Hopefully this very beneficial for you all, and you can attend in the keynote speech, and also you can discuss with them, the keynote speaker, the expert in their field, including the magnetic and also the functional oxide, and also artificial intelligences, and also electronic devices. Finally, I would like to express my thanks to all who have helped to support Icopia this year. And we hope you all enjoy the conference today until the end. This conference is the one-day conference. So the first is the the plenary session, and the after break is the parallel session. So thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Nuryani. We are now going to listen to the welcoming speech by the Vice Rector of Academic Affairs, Universitas 11 Maret, to open this conference officially. Ladies and gentlemen, please welcome Professor Ahmad Yunus.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. The Honorable invited speaker, Professor Muhammad Khairul bin Ahmad from University Tun Hussein Un, Malaysia. The Honorable Professor Didier Vasquel from Université de Littoral Côte d'Opale, France. The Honorable Dr. Steve Ling from University of Technology, Sydney, Australia. The Honorable Professor Budi Purnama, speaker from Universitas 11 Maret, and distinguished the Dean of Faculty of Mathematics and Natural Science, Bapak Dr. Harjono, and distinguished all of Vice Dean, the Head of Department of Physics, and also the researcher in Department of Physics, including Professor Ari, Professor Tri Atmojo, Professor Marzuki, and the colleagues. At this precious moment, let us first express our gratitude to the merciful God who has granted us with blessing and grace that we could gather here today to attend the 10th International Conference on Physics and its application, which is here organized by the Department of Physics, University of 11 Maret. Let me extend my warm greeting and welcome to our distinguished speaker and participant, particularly those from abroad. Distinguished guests, ladies and gentlemen, really we prepare Icopia conference since last year, but due to the COVID-19 pandemic, we are very sorry that we had the Icopia conference by online. But we don't reducing our enthusiasm for sharing, and we hope that this Icopia conference can be a trigger to raise the level of our research to better level. Ladies and gentlemen, this conference is an important event. It is our occasion for positive contribution, ideas, and knowledge sharing regarding to the development of future physics and its field of application in Indonesia, including in field of material physics, theoretical and computational physics, instrumentation, optics, acoustic, and geophysics. In this university, I think all of department every year they conducted the international conference to become better in our academic reputation. And as you know that the Universitas 11 Maret is the 11th top university, national university in Indonesia. Finally, I hope all participants of this conference can find important areas of common ground on the best way for achieving the broad goals. I have great pleasure in formally declaring in the convention open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Ahmad Yunus. Next on agenda, we will have a photo session. Please to our honorable speakers and all of our participants to turn on your camera. For slide 1, slide 2, slide 3, that's enough. Thank you. Excellencies, ladies and gentlemen, we will begin the first session of the plenary lecture that will be led by our moderator, Dr. Ahmad Marzuki, an assistant professor from Physics Department, Universitas 11 Maret to carry this session. Please welcome Dr. Ahmad Marzuki.
Assalamualaikum warahmatullahi wabarakatuh. Good mornings, ladies and gentlemen, wherever you are. You can now join our conference, Icopia, while sitting in your house, enjoying your morning coffee or tea. Okay, I hope you are very well now this morning, and I hope everybody in your family and maybe most of us are very well. Okay, ladies and gentlemen, there are two great speakers now have joined with us. They are Professor Muhammad Hairul bin Ahmad from University Tun Hussein on Malacca, Malaysia. And the second one is the Dr. Steve Links from University of Technology, Sydney, Australia. Ladies and gentlemen, time allocated for this session is 1.5 hours. That is 30 minutes is for Professor Hairul, 30 minutes is for Dr. Links, and another 30 minutes is for question answer. Okay, before Professor Hairul deliver his talks on rutile phase TiO2 nanostructure toward electronics devices applications. Let me introduce briefly for him. Okay, Professor Muhammad Hairul bin Ahmad is from Department of Engineering, Electronics Engineering, Faculty of Electrical and Electronic Engineering, University Tun Hussein on Malaysia. He is currently working on microelectronics and nanotechnology, Samsudin Research Center, and now, he is a Deputy Director, Research Management Center, University Tun Hussein on Malaysia. Professor Hairul, are you ready for delivering your talk now?
Okay, I'm ready.
Okay, please welcome Professor Professor Hairul bin Ahmad to present his talks on rutile phase TiO2 nanostructure toward electronic devices application. Professor Hairul's time is now yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay. First, I'd like to thank Dr. Ahmad Masuki for introducing me to the audience and to the speakers. Alhamdulillah, I would like to thank the organizer, Icopia, for inviting me to share a little bit of my research. Thank you also to the Honorable Vice Rector of University 11 Maret, Professor Dr. IR Ahmad Yunus, and the Honorable Dr. Nuriani, and I think my friend Dr. Agus Suprianto, which I met I think last year in my lab. Okay, it's very grateful that I become one of the speakers because I could share and about my research and a little bit about my university. I think, but I think I've been to University Supermarket. I think 2017 is not mistaken. Together with my colleague, Dr. Nafa Rizal, Dr. Zainizan, I think Dr. Professor Agus know about this, or other researchers maybe remember me, and our friends. Okay, today I would like to share a little bit of my research. My title is about rutile phase Ti2 nanostructure towards electronic devices application. So I think when we are in a physics area, oxide materials such as TiO2 is not it's a not rare thing. It's a common thing about TiO2 because people are doing more research about TiO2, not only for electrode devices. They also extend it to other application. Okay, from the introduction from Dr. Ahmad Mazuki just now, currently I'm as a not only a researcher in our center in microelectronics and nanotechnology, I'm also working as a deputy director in research management. So we handle grants from the national and from the international grants. So we are handling all the grants for the staff. Okay. MIN SRC, we call it MIN SRC, is a microelectronics and nanotechnology. So we have many types of nano or micro technology there in our center. Okay. Okay, this is the outline. Okay, before that, let me explain about a little bit of TiO2. I think I'm focusing on electronic devices, but there is also some application that I want to share with you all. Not only electronic devices, but now we are also using it in wastewater treatment for the environment purpose. So the introduction, let me explain a little bit about my university. Okay, about my center a little bit, maybe 10 minutes about that, and then some literature review about rutile phase TiO2, and then the advantages of the nanostructures material, and then the publication that I have done with my colleague, with my group, during my PhD and after I came back from my PhD, methodology, and then result and discussion, the explanation or the result that I have prepared, that I published for electronic application for wastewater treatment, and some of we try to use the same material in ceramic production. So I will tell you and share after this. Okay. And then lastly is a future project, means what I'm going to explore in my lab after this. All right. So the introduction about University Tun Malaysia. Okay. This is our library. They said that our library is the largest, is the biggest library in Southeast Asia. I don't know. They said like that. Okay, this is our library. Okay, our chancellor or vice chancellor office in on top of the building. Okay, our campus, our university is located in Johor State. It's southern of the Malaysia. It's near to, I think, near to Sumatra. Okay, and then it took about from KLIA to our university is about 3 hours driving. To Singapore is about 1 hour driving to the airport, to the Singapore airport. So if you think usually researcher or student from Indonesia, they come here by using the Senai airport located in Johor Bahru. Okay. Okay, this is the entrance of the University of Malaysia. We have library, just now I said. We have a postgraduate and international office. And then they have library complex. It's the labs for the faculty located all here. They put in one area, which is all the, this is lab for mechanical and electronics department. Okay. Okay. In Malaysia, we have 20 public universities now. Okay. Among 20 universities, there is three types, sorry. We have RU's university, it means research university. We have a comprehensive university, and then we have technical universities. So we as a UTHM, we are a technical universities. We are not from research university or comprehensive. We are technical universities. Among these technical universities, we have 4 universities. We have UTM in Malacca. We have University Malaysia Pahang in Pahang State, and University Malaysia Perlis in Perlis in the northern part of Malaysia. So our niche area or our aims, our vice chancellor said that we as a technical university must have a good technical knowledge to produce or to assist the industry around the campus or around in Malaysia. So our target is to help the industry, not only small or medium industry, but all the industry that they need help from us. And then we have one niche area that we declared just this year. The niche area for our university is sustainable technology and transportation. Okay, if you look at the website of our university, we're going to have a railway department to be open. I think they already recruit students. So our niche area for university is about more on transportation and sustainable technology. So that's our new area that we have to explore and to strong in it. Okay, so we have 2 campus right now. We have in Pirate Raja. It's a very in Malay we said very kampung. We are not in a city. It's located in kampung in Pirate Raja. And then we have Pagoh. Okay, Pagoh is a new campus where the Faculty of Science and Faculty of Technology Engineering, and then we have the Department of Diploma Studies. So three faculty there that serve about 6,000 students. Now in Pairaja, we have about 11,000 students. So total is about 16 up to 17,000 students in UTHM. And if you look at UTM campus, TG is Tanjung Labuh. Tanjung Labuh is one of we're going to explore more for aerospace or piloting there. We already have the space, so we're going to have airport, a small airport there for our students we have piloting and we have engineering, means to repair plane. So we have the program down in our campus in Tanjung Labu. Okay, okay, this is the campus. We have 9 faculties. Okay, in our university, so students. Okay, this is the rating. This is it's old one. I didn't get the new one. So okay, we have 5 stars in QS rating. Okay, but we are still developing to get higher ranking in the Asia. Okay, international student mainly from the Middle East. We have Iraq, we have Pakistan, we have Nigeria, UAE, and Yemen. Okay, and so from Indonesia also, we have many students from Indonesia. Okay, okay. For research and innovation, so we have, okay, just now I said that I'm in MIN SRC, Microregion Engineering. We are one of the center of excellence in our university. So we have the 3 more Advanced Manufacturing Material Center, MMMC, and then we have also Research Center for Applied Magnetic and Industry Center, Railway, and then TVET. Okay, this is it's a 2 research center, the Railway and the TVET. So our university also now champion in TVET. So they are developing a quite good facilities here in Malaysia in Indonesia. And then if you look at the center of research, we have also some other center of research. The center of research is located under the faculty. Center of excellence is directly below of the Deputy Vice Chancellor of Research and Innovation. Okay. So this is a big view of our university, University Tun Nusrat Malaysia, and our my lab, MIN SRC, is located there. If you look at, we have a library. Okay, we have mosque. This is the, if you look at, this is our convocation hall. Okay, this is the rounds. Okay, you see the round, then this should be a faculty. All the faculty will have a building. This is the electrical electronic building. We have civil, we have education, we have a management, we have a medical there, and then we have also faculty of computer science. Okay, so we are developing to become a big university, maybe around 10 years after this. Okay, for this is the members of our center. So I'm one of the the principal researcher in our center. So for your information, there is 3 good students, very hard-working students came to my lab last year. Diani Galih Saputri, Nadia Elhaq Diana Hesa, and Fabrina Ramadani. The 3 good students came here. They about 1 month, a bit more. They came here, they studied, they managed to do experiment. They got their result, very good result. I think, if not mistaken, they published the result already. And Dr. Agus also came here, and then we have a discussion. Okay, so it's a very good opportunity that for the student. Hopefully, if there is other student who like to come to my lab, okay, please tell me, and then we have a good collaboration after this. So this is the condition part. So this is the information about our center. Mainly, we are the members in our center is most of it is graduate from Japan. So the culture in our lab is more towards Japanese style. We have a lab, we have a student will sit in the lab, do the research in the lab, and then we have the progress report meetings, so on. And then all the equipment located in our building, so we shared our facilities there. If you have time, you can look at the Min SRC homepage, min-m.edu.my. Okay, it's a very established, so we have many characterization method or equipment there. Okay, it's a quite good kind of facilities in our lab. Okay, so now we go into our research. Okay, it's about TiO2. I think many of us, some people said titania, and then why we are using titania, rutile phase titania instead of anatase. Okay, usually people use anatase phase of TiO2 in many applications, but I think when I started doing this while I'm doing my PhD. So instead of anatase, there is one other one other phase that in TiO2 they call it rutile. They also have brucite. Okay, but brucite is not quite practical use in for electronic devices or other application. When I look at TiO2, okay, it's a good material, it's stable in and to chemical, but people ask at that time, people are try to make from anatase. Why not rutile? If you look at rutile, okay, the comparison between rutile, it has a better in good in electron transportation compared to anatase. Okay, it's a very stable. It has higher refractive index, okay, and a good in light scattering. So means the advantages is there, but people are not using it to other applications. So I'm thinking, why not we prepare this material using a simple method. I think the drawbacks or the problem in rutile is when we prepare, you have to prepare at a high temperature. We have to prepare until 900 degrees Celsius. This is the problem that people face when we are trying to prepare the TiO2 rutile phase. Because anatase we easily can prepare at 300 or 400 degrees Celsius, but for rutile you have to annihilate at 900 degrees Celsius. So this is a problem. But if you are using a simple method, I will explain to you the hydrogen method. We can prepare the rutile phase at 150 degrees Celsius using the hydrogen method. It's a very cheap, it's a very simple method to prepare. So with this motivation, with this idea, I proceed and then I try to make a nanostructured material using this method. We know that nanomaterial, when it is in a nanomaterial, in a nano size, they had a very different characteristic. So why, okay, we have a TiO2 nanostructure, we have nanoflower, we have nanorods, we have nanofiber, we have a nanowire. So why we are going to use this? One of the reason is because it has a good electron mobility. So nanostructure produce a very good electron mobility. So okay, why not we try to combine? Okay, we have a nanorods, for example, it has a good electron mobility, but it has a lower surface area. Okay, for nanoflower, for example, we have a high surface area. It's a larger particle size compared to the nanorods. So why not? Okay, what if we combine? Why not we combine the nanoflower and nanorods? Okay, at least in my studies, when I did my PhD, I combine these two materials. I produce these two types of material in one method. Using one method, hydrogen method, I can produce this both nanoflower and nanorods. For this material, I use and I characterize, I prepared dicystite solar cells that I will explain you after this. Okay, what we get from this material, okay, when we have nanoflower, of course, we have high surface area. From nanorods, we have good electromobility. So we have good, we combine this material and then we have two benefits. Okay, the problem is, okay, the high temperature and the interconnection. High temperature means that we have to prepare at high temperature for rutile. But in hydrothermal method, we have no problem. We have to do for about 150 degrees Celsius. And then the interconnection. Okay, the interconnection, actually there is a little bit barrier from the nanoflower to the nanorods. The connection, the interconnection between this one. So this is it might be some problem in our when we are configure electronic devices. Okay. So some of the means the proof that rutile phase TiO2 is a candidate, is a good candidate for electronic devices. So this is the paper that I and my colleague and my group and my student have prepared and published. So we have TiO2, that's flower like TiO2 on top on glass substrates. Okay, we publish in Metal Letter. We have general in ceramic. We have high voltage ultraviolet UV sensor device. Okay, using our nanorods only, we managed to develop UV sensor. Okay, so this is already published in this year by my PhD student. And then my colleague and my master student also try to dope the TiO2 nanorods. This is all the rutile phase TiO2 nanorods, not anatase. I'm not interested in anatase. I'm focusing on rutile phase TiO2. And then we try to collaborate, okay, to try to use this TiO2 nanostructure, the rutile phase for thermoelectrics. Not only sensor, not only for solar cell, we also they also have a potential to use for thermoelectric. So this is published last year, and then also for the DSSC, we try uh, to mix with the graphene to enhance the performance of the solar cell, and then we try to we try to mix. Okay, we try to improve the TiO2 nanostructure, and then we publish it also, mainly for the SSC, but also we try also to, the last paper we studied Raman for our, we studied TiO2 nanorods and nanopowder. We study the characteristic of the TiO2 nanorods and nanopowder of Raman. Okay, so means that the problem is not for the material. It means it shows that the TiO2 rutile phase TiO2 can be prepared for electronic devices. So now I share to you how we are prepared the TiO2 nanorods and nanopowder. It's a very simple method. We use a Teflon, and we use the chemical, and then we mix, and then we mix the chemical, and then we put into the oven with specific time and temperature, and then we rinse, and then of course we can anneal, or then we get the thin film. Okay, this is very simple. It's a low cost preparation method. What you can get from this is the TiO2 nanorods and nanoflower on top of it. Okay, actually we can change this recipe, the chemical, the concentration. We can change the temperature, the time reaction. It will change the morphology of the nanostructure. So it depends on what application that you want. If you want to prepare a sensor, just now I said that the problem interface with nanoflower and nanorods. So we find out that if you want to use for sensor, the nanoflower is not suitable. So we have to prepare only nanorods. So we have to change the recipe until we get only nanorods only. But if you want to have a good result we want to use the surface area, we must have the nanoflower on top of nanoroots. That's a study I prepared when I did my PhD. On top of nanoroots, we have a nanoflower. It enhanced the performance of the solar cell that I prepared, DSSC, the dye-cell solar cell. And then after I finished PhD, we try to harvest, we try to get the nanoflower. I will show you the same image of the nanoflower. It's a very good nanoflower. It's a very, it's very high surface area. After I got my PhD, I think how we can harvest the nanoflower only. We don't want the nanoroots. Of course, if you want the nanoroots only, we can change the recipe. But what if we only wanted the nanoflower? So it's very simple. We just take out the substrate. We just take out the substrate, and then we can get the nanoflower. But the problem is the yield is so low. It's too low to get the nanoflower only. But if I have we managed to get a high yield, but we have to prepare a very big vessel for the hydrothermal method. So that one will be costly, but we are trying to prepare a large yield for the nano flower for various type of application. So after this, I also tell you what I'm doing with this nano flower. So using this method, the same method, we just take out the substrate, and then we can get the flower. So this is what happened in the autoclave. In early stage, okay, the chemical is dispersed. So the growth we start on top of the FGO, and also the solution also the particles start to agglomerate and it turns to the nanoflower. In the middle stage, so we can see in the middle stage means for example we prepared 10 hours of hydrothermal method. The first 3 hours is the nucleus start on top of the FGO. In 5 hours, they have a small nanoflower dispersed in the solution and start growing on top of the FGO. And after 10 hours, for example, we can have a nanoflower on top of the nanorod. So this is the beauty of the research that I have done. So we have two type of nanostructure. Using just one time of method, we can have two. And just now I said that if you change the recipe of the chemical, we can have only nanorods. Okay, but if we take out the FTO, we can get the nanoflower. So this is how we manipulate, manipulate to get these two type of nanostructure. It has a benefit, okay, when we have two, yes, we have nanorods also we can use in electric devices. Nanoflower also we can use for other applications. So this is the beauty of the research that I have done. So, okay, some results, okay. For electronic devices, I've used these nanorods and nanoflower for my PhD study for dye-cell solar cells. Okay, and then after I graduate, I asked my master student, and now she's in Japan for double degree program in Shizuoka University. She's a full sponsored PhD student there doing also UV light sensor. So she continued with the UV and tried to dope with other metal dopant. So she's doing UV light, and then for the ethanol sensor, this is my master student currently doing this. So we try. Okay, just now I said that for my DSSC, we have to have nanoflower to get the dye absorption. With dye absorption, we can increase the performance of the DSSC. Okay, so when going to use for UV light sensor, we don't need the flower. We have to use the nanorods only. For ethanol, yes, we have to have both. We are trying to use both nanorods and nanoflower, but still study. Okay, okay. This is just now I said just we use butyl oxide as a precursor as hydrochloric acid. This is the normal that I think people have done many more in the SSC. So this is my when I did my PhD, we got a very line rutile phase TiO2, and then we do second preparation. Okay, just I go through. I just to share the ideas or what I found until now about the rutile phase TiO2. So this, if you want to look at the result, you can see in my paper, I told all about this result. Okay, this is the this result from my PhD studies. Okay, then we have this. Okay, so it's a very high surface area. We have a nano flower like this. So imagine how much dye that can be absorbed. Okay, this is the result. We have about 4.2% of efficiency in dye-cell solar cell. Okay, now we are going to the UV light sensor. This is the diagram that my student have prepared. We are measuring the UV sensor. 30 minutes?
You have 5 minutes more.
5 minutes more. Okay, thank you. Okay, this is for the UV light. Okay, we have response there, and then this is for the ethanol sensor. We prepared using the only nanorods, and then we measured using this setup. This already also published in one of the nation's journal. And then this is the nanoflow that I told you. We try to, we're still considering to use the nanoflower in our ethanol sensor. So it's still in understudy, but we try to confirm it a little bit later. So, and then this is the result of the sensor. You can see that actually flower may contribute to the electrical properties of the sensor, but we still understudy. See, it's not a good result now, but we still studying it. Okay, and then we use. Okay, this is what we are now trying to. We are trying to use the nanoflower powder for palm oil mill influence. So we have so many companies in palm oil companies in Malaysia. So they have a problem of coloring. When they dispose the wastewater, they have a coloring problem. So we're going to use this material to overcome the problem in our palm oil company. Okay, we are using nanoflower. Okay, same. The method is same. Okay, we tried. This is a metal blue. We tried also for using the metal blue. Okay, this is the flower that I said. We are trying to using it different shape. Okay, this is the gradation we study. We have about 45% of degradation, and then the highest is about 60%. Okay. And also we try to use rutile phase as a binder in cracking. So in ceramic production, they have cracking when they need the product. So we want to use this flour to chillate or to get to hold the material, not to be a crack in the product. So we put into this product into the ceramic so it can enhance this is a flour that I prepared for the ceramic. It's we still understudying its investigation. So it's a good potential for the cracking, to avoid the cracking in the ceramic products. Okay, the surface area. Okay, this is the okay. Future product, project we're going to use for thermoelectric. If you are any collaborators, we are trying to use, and then it's shown that it has a good effect in thermoelectric. And I also one PhD student are doing mechanoluminescence for MEMS application. It's not a TiO2, but it's a good material that we find out is a mechanoluminescent, means that powder or material, when we uh, give some stress, it emit light. So it's good for MEMS application. And then one of my new PhD student doing a biopolymer gel electrolyte for diesel solar cell. So we try to prepare a very good gel electrolyte, not only for solar cell, for other electronic devices. And now, okay, conclusion. Okay, rutile phase. Okay, we can have a contribute to manipulation film or powder. Okay, we just try to change the morphology of the TiO2 nanostructure. It's may used for amplification, and then yes, not only anatase, rutile also is a good candidate for electronic devices. Others oxide material. We have zinc oxide, we have a magnesium oxide. So TiO2 rutile phase also one of the candidate now that we are going to use in the application. So I would like to thank. This is the last photo session, I think, from with Dr. Agus and the three students, Dr. Diani and Nadia and Fabrina. Okay, this are my student. Okay, this is last year photo session. Okay, thank you very much.
Okay, thank you very much, Professor Hairul. This is really very great lecture, and it's very, very useful for us. Okay, Professor Hairul, would you have a question answer right now or after Dr. Steve Lee's lecture?
If I may, can I have the question right now, because I have another meeting 10 minutes after this. Can I have a question right now?
Okay,
Sorry.
yes.
All right.
Okay, ladies and gentlemen, we have 10 minutes for question answer. So please, everybody who have a question can write at the notes in this Zoom, or you can raise your hands and ask your question right to Professor Hairul. Okay.
Ahmad. Dirisa nih, Pak Ahmad.
Yeah.
Okay. Before that, so if there any other student who like to come to my lab to do lab as a Diani and Nadia and Fabrina, is welcome. You can send me email, and then maybe after COVID, okay, maybe next year, if you have other students want to come here, please, we open for the collaboration.
Okay, Prof. Hairul, if there's no question from the audience, I have one question for you.
Okay.
Prof. Hairul, what is the key difference between the method for producing nanorods and flower rods? The key difference between the method that you use to produce nanorod and flower rods.
You mean the material that I use to prepare this nanostructure?
The difference process. I mean, what? Yeah.
It's a same process. We do the hydrogen method. Just now I told you, after we put all the chemical in the autoclave, we put in the oven.
Yes.
After 5 hours or 10 hours, there will be a nanorods and nanoflower on top of the nanorods. It happened in one time. It's grow 2 types of nanostructure in one time.
So they are from the same crystal structure, like this.
Sorry.
They have the same sort of crystal structure. I mean, between the flowers and rods.
Yes, it has the same crystalline structure. It's all TiO2 rutile phase in SRD. There is no anatase, but yeah, the orientation is a bit. If you have a nanoflower, of course, it's a bit, but it's a rutile phase. That's the beauty, you know. I think if we change the time and the concentration of the solution, you can get, for example, just said now, we can get only nanorods, aligned nanorods. If we play with the time and we play with the concentration of the TiO2 or the solution. So yes, it's a good rutile phase TiO2. Okay.
Okay, thank you very much, Professor Hairul, and it's very good to
Ahmad,
ya.
to ask to Prof. Khairul.
Oke, oke.
Yes.
Siapa? Silakan, Pak. Oke.
Pak Khairul.
Yeah, yeah.
Yeah, this is yeah, interesting results because usually other researchers work an atas pace, right?
Yeah, yeah, yeah.
But you work about rutile paste. Because it's a wet process, I think this is not easy to control.
Correct.
About reproducibility. How about reproducibility?
As long as you use the same, the possibility is for me when I did my PhD, it's no problem. Okay, but you have, before that, before you prepare do the experiment, you have to make sure the autoclave is again good condition, means the cleanness of the autoclave. We because yes, you are correct, doctor. This is a wet fabrication. The probability, the reproducibility is a problem. But for me, I said to my student, the before you do the experiment, make sure the autoclave is in good, is a clean, because we are using wet. So we make sure the beaker, the autoclave is in a good condition, and then use the parameter. Do not change the parameter. Start from the beginning until the end of your study. So this is the precaution that I have to. I asked my student, and if there is a it's not no, the result is not as we expected, so I will ask them to do again to make sure all in a complete arrangement.
So how about interconnection or interface between a nanorod and nanoflower?
Mm-hmm. Yes, the interface is a very is going to have a problem, but how we can to overcome this problem, the interface, we have to do, okay, just now I said that one step of hydrothermal, we can have two nanostructure, but we can solve the problem by use two steps. So first step, grow the nanorods only, and then try to put one very thin layer of TiO2 anatase, okay, and then do the second hydrothermal method to grow the nanoflower. So after that, we can anneal, and then we can eliminate the problem between these two interfaces.
Is it possible to change the first nanoflower and then the next stage nano rod?
Yes, because as just now I showed you our the very small nanostructured nanoflower. That is an experiment that I have two times. First hydrothermal, I get a nanoflower, a nanorod, sorry, and then second hydrothermal method, second hydrothermal process, I managed to have a nanoflower only. So this is how we can get is we try to manipulate the time. Right? We tackle the time, and then we find a suitable, and then we can get the nanoflower only.
Okay, thank you, Dr. Haidar.
Yes.
Okay, thank you very much, Dr. Risa Suryana and Professor Hairul. Ladies and gentlemen, if you have any question, please write down your question in Zoom group chat below the screen, and we will pass that question to Professor Hairul. Okay, thank you very much, Professor Hairul.
Okay, thank you very much.
Thank you very much. We will see you again next time, hopefully, and we have another maybe student or collaboration with you. Okay, thank you very much.
Okay, thank you very much. Assalamualaikum
Okay, thank you very much.
warahmatullahi.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, ladies and gentlemen, these are the presentations from Dr. Professor Hairul. And now we go to the next presentations. This presentation is about deep learning for biomedical application that will be delivered by Dr. Steve Links. Okay, before Dr. Steve Link delivering his talks, I want to introduce him briefly. Okay, Dr. Steve has worked extensively on design and analysis on computational intelligence technology since 2000. He has MPhil and PhD in electronics and information engineering from the Hong Kong Polytechnic University HKPU. In the year 2006 and 2007, he had worked as research associate in School of Electrical, Electronic and Computer Engineering, the University of Western Australia. He joined the University of Technology Sydney as Chancellor Postdoctoral Research Fellow and lecturer in 2009 and is now senior lecturer. Being an active researcher, he has published over 130 research papers on artificial intelligence and its application. He is now active in the International Society. He has been a senior member IEEE since 2013. Okay, Dr. Steve Links, time is now yours.
Okay, yeah. So, so I will share my screen first. Okay, can you see my screen?
Yes, yes.
Okay, yeah. So I'm happy to give this lectures. The topic is deep learning for biomedical application. So there's some about me. So friends already introduced for me. Okay, so firstly, what is artificial intelligence? So we can see that the AI is a very hot topic. It is a methodology in modern computing that provides system with the ability and deal with new situations such as generalization, discovery, association, and attraction. So in the AI, one of the key domains is called computational intelligence. So in the computational intelligence, which involves three main components. So the first is a fuzzy system. The second one is the neural networks, and the last one is called the evolutionary computation. So what is a fuzzy system? So fuzzy system is a logical system that is much closer to the human thinking and natural language. So it contains a set of if-then rule with fuzzy membership. So the key attributes of the fuzzy system is the fuzzy system is able to make a decision. So for examples, okay, if we have two inputs, if the input one is high and input two is low, so looking at that, we can use some natural language to represent the level of the inputs. So when we decide the input and what's the input, then we can generate the output is also with some natural language. For examples, if the input is high and input is low, two is low, then the output is very high. So we can see that in this fuzzy system, it is able to reasoning based on the greatest knowledge. The key second component of the AI is the neural networks. So neural networks has generalization and recognition abilities. So neural network is able to learn when we provide the training sets to the system. So looking at that, in recent news, a hot topic, hot areas in neural network is deep learning. So the deep neural network is able to handle a huge input, such as images. After the learnings, a set of the features of the image, or other application can be extracted. So in this speech, convolutional neural networks, especially the neural net, I will introduce in this session, which is one of the deep neural networks. So we have another component of the AI. It's called the evolutionary computation. So it is a global optimization method. So based on this figure, we can see that. So all of them, they can link with together. For examples, we can use the evolutionary computation to optimize the parameters of fuzzy system and neural networks. We also can combine the fuzzy system and neural networks together to form a neural fuzzy system, which means that this neural fuzzy system is not only have the learning abilities, it also can make a decision. So basically, neural networks are information processing system. So it looks like a black box to accept the input and produce the outputs. So there are some applications by using the neural networks, such as classification, pattern matching, noise removal, optimization, and control. So in the classical neural networks systems, so we have this classical multi-layer feed-forward neural networks. So in this multi-layer feed-forward neural networks, we have the input layer, hidden layer, and output layer to form a neural network. So the main objective of the neural is how to optimize the weight, based on the input-output patterns. Now, what is the difference, between the regular neural networks, as mentioned before, and the convolutional neural networks? So convolutional neural network is just one of the deep learning methods. So we can see that convolutional neural networks are similar to regular neural networks. They are made up of the neurons that have the learned weight and bias. It's also, each neuron receives some inputs, perform a dot product between the weight and inputs. So you can see that this concept, the CNN is same as regular neural networks. However, there are some significant difference compared with the feed-forward type neural networks and CNN. So we can see regular neural networks doesn't scale well to full image. For examples, if we have the image size is 32 times 32 times 3, so talking that we handle a color image. So that's why we have the 3 color channels. So we have the image size is a 3D volumes. So a single fully corrected neural network, in the first hidden loop will have 3,000 weights. We are just talking about, if we have 32 times 32 times 3 inputs, correct with the single hidden nodes, we already have more than 3,000 weights. So you can see this amount still seems manageable, but clearly the regular neural networks does not scale well to large image. So we give another examples. If the image, is a large image, for example, 200 times 200 times 3 pixels. So we can see that the total number of the weights, correct with the single neuron in the hidden layer is around 120,000 weights. So we can see this is a very huge number. This fully corrected is wasteful and huge number of parameters would quickly lead to overfittings. So to overcome these problems, we have convolutional neural networks. So the convolutional neural network takes advantage of the fact that the inputs consist of image and contain the architecture in more sensible ways. So a NN is made of the layer. So we have different layers. So each layer, they have a simple application program interface. Okay, it's used to transform an input 3D volume to an output 3D volume because we handle the color image. So looking at in the different layer, some layers may have some parameter to adjust the system. Some may not have the parameters. So it is a classical architectures of computational intelligence. It's a convolutional neural networks. So looking at, we have the input image. Okay, so for the first layer of the CNN is called the convolutional layers. So in this convolutional layer, it's used to compute the outputs of neurons that are correct to a local regions. It's computing a dot products between their weight and small regions they are collected in the input volumes. So looking at, for the CNN, the weight are sharing for whole image. Okay, so I will introduce later. So that is the key contribution why the CNN is able to handle a large image rather than using the conventional neural networks. It is because their weight, okay, is sharing for whole image. So after that, after the convolution layer, we have the pooling layer. So pooling layer is simply to downsampling the image. Okay, so we can see in these examples, for the first convolution layer, the size of the image is 28 times 28. After the downsampling by the factor of 2, the image is reduced to 40 times 40. So looking at that, why we call it is a deep learning, because we can repeat, okay, we have to repeat all the procedures of the convolution layer and pooling layer. It depends on the application. So we can have a deep structures. So after the pooling layer, okay, we have the fully collected layer. Okay, this is same as the conventional regular neural networks, which is used to compute the class scores. And finally, we have the softmax classifier. So the softmax classifier is based on the class scores in the fully collected layer, then based on the probability to classify, okay, each class. So in summary, it is a basic CNN structure, including, okay, convolution layer and pooling layer. So usually between the convolution layer and the pooling layer, we have the rectified linear units. It is a transfer function, okay, used to transform the output of the convolution layers. And finally, okay, we will use the probability to represent the different class. For examples, now we have the image, okay, it is a trust. Then we can use this deep learning structures to classify the image is either trust or car. So in some examples, for this example, the output, okay, can be the probability. So we say that the system will tell you that it may have a 60% is classified as a trust. So again, why we call it is a deep structures, because we can repeat, okay, we can repeat all the procedures with different parameters. So we can have same structures, but we can have n convolution layer and n pooling layer to apply to different applications. Now, I would like to provide some briefly concept for each layer. So the convolution layers, okay, is the core building blocks of the convolutional networks. That does most of the computational heavy lifting. So as mentioned before, in the convolution layers, okay, all the weight, okay, is shared by the whole image. For example, we have this visual size is 5 times 5, okay? Because it is a color image, so it is a 3 dimension. So we have the weight is equals to 5 times 5 times 3, because we have the 3 color channels. So looking at, for one filter, we only contain 75 weight. So we will use this same weight, 75 weight, to scan whole the image, okay, for this layer. So unlike the before neural networks, okay, each input pixel, okay, we use a single weight to represent. But for the convolutional neural networks, we can share all the weights. So it's to save a lot of the parameters. And also, the convolution layer is called the local connectivity attributes. So in the convolutional layers, we can have many filters. It depends on the user. For example, we can define, okay, in this layer, we have 24 filters. So each filter is 2 times 2. Then we can virtualize, okay, in this application, we have this choice. If we have 24 filters with different parameters. So we can see we have this 24 feature map. So looking at that, the convolution layer is used to extract the features of the original image. So with this, okay, we can extract the image with a different edge or a different color. Okay, it depends on the filter. So finally, the weight of the filter will be treated by the system. In the second part is the regular rectified linear units. It is such a simple activation function because after the convolution layer, after to apply the filters, sometimes the outputs can be negative values. As we know that to represent a color pixel, it should be positive values. Then we just simply apply this rectified linear units to ensure all the negative values to become zeros. Then we can, okay, use this the output value to represent an image. So after the convolution layers and rectified linear units, we have the pooling layer. So the pooling layer is just simply to, okay, downsampling the input volume. So after that, we have the fully connected layers. So before the fully connected layers, okay, we still have the image, okay, like this. So after that, we need to flatten to be a single vector. Then we using the conventional fully connected layer, then we can compute the score of the class. And finally, we use the soft layers. So soft layer is just a simple transformation to transform the score, okay? This is the output of the fully connected neural networks to be a probabilities. So finally, the system, okay, can use the probability to represent. So in the convolutional neural networks, so one of the application, okay, the hot application is the segmentation. So the segmentation is used to segment the object or the part of the objects. So there are 2 types of the segmentation. One is the instance. Okay, this is treat the multiple objects of the same class as a single entries. And other is semantics. For this semantics segmentation, it treats the multi-objectives of the same class as distinguished individual objects. So it is more challenge and more many industrial application is belongs to this type. So to solve this type of the segmentation, one of the hot technologies, okay, in the deep learning is called the UNet. So UNet is a convolutional neural network, okay? It is used to develop for biometrical image segmentation. So the advantage of using the UNet is it is a convolutional neural space. That means the network is based on the fully convolutional networks, and its architecture was modified and extended with fewer training image. So it is a advantage because sometimes for most application, we may not have enough training image. Then by using the CNN, this is able using fewer training image to generate a precision segmentation performance. And also, okay, the flexibility of the inputs. because for the UNet is the end-to-end fully connected networks, such as it only contain convolutional layer and does not contain any dense layer, because of which it can accept image of any size. So why we need a UNet? Okay, because the UNet is end-to-end settings. So we can use this image, okay, input image. So for the UNet, we can generate the same size of the image with some segmentation outcomes. And most important is for the UNet, we just need to use a fewer image to train the UNet model. So it is a typical UNet architectures. So that's why you can see it is a U shape. So for this typical UNet, okay, which in you can see that the blue box is corresponding the multi-channel feature map, and you can see this the whiteboard here that you just copy, okay, from here. It copies this feature map to this layer. So for the UNet architectures, usually we can separate into 3 parts. The first part we call is the contracting or downsampling path. Okay, in this contracting path, it consists of 4 blocks. Okay, 1, 2, 3, 4. So each box is composed of 3x3 convolutional layer with activation function, and also including 2x2 maximum pools. So in this downsampling path, we can see that the number of feature maps, okay, is double at each pooling. Okay, the first is we have the 64 feature maps. In the second box, we have the 128 feature maps, and so on. So the purpose of this contracting path is to extract the context of the input image in order to be able to do the segmentation. So the second one, okay, is called the bottleneck. So this bottleneck is just between the contracting path and the expansion path. Okay, just directly to move the image from downsampling path to upsampling path. And the last path, okay, last part is the upsampling path in here. The purpose of this expanding path is to enable precise localization combined with the contextual information from the construction path. So in this part, we can see that, okay, the number of the feature map is decreasing, and also the image size, okay, is go back to the original size. So finally, we can see that the input image and the output segment image should be same size. So there's some examples, okay, by using the UNet to track the cell tracking. So that is we have this training image, okay, used for training. So to train the UNet, we need to have the ground truth. Okay, this is like the decided response, what we want to segment. So we're using the training image and the ground truth. Okay, we can train the UNet. So after that, we have another testing image like this. So we can put this testing image to the UNet. Then we have this predicted output. So this is one of the example by using the UNet. So in this talk, okay, I will introduce 2 real biomedical applications by using advanced deep learning, especially focused on the convolutional neural networks and UNet. So the first application is called the multi-level convolutional neural networks for tendering lung nodules classification. So the lung cancers, okay, is one of the 4 major cancers in this world. So the 5-year survival rate of the lung cancer is only 80%. If we can diagnose and treat in the early stage, the 10-year survival rate can reach to 90%. So we can see that if we can have some effective method to diagnose the lung cancer in early stage, it is very significant, okay, to increase the survival rates from 80% to 90%. So it is the motivation of this research. So we need to see how to develop effective methods to diagnose, okay, the different stage of the lung nodules. So we have this lung nodule CT image. So generally, the CT image is a main and most effective method to diagnose the lung nodules in the early stage. Okay, while the interpretation of the CT image are mainly carried out by doctors. However, they are limited by the human subjective, large variation across the interpreters and physics. So therefore, it is significant to use the CAT system to assist the expert referrals for the early diagnosis. Okay, so the aims, okay, in this research, we want to classify the lung nodules in which status, benign, okay, indeterminate, or metastasis. So we have using the this is the basic framework, okay, of the system. So firstly, we have the original CT image. Then we have some pre-processing to chop the noodles and resize it to be ensure the dimension for all pre-processed pictures are the same. So we need to chop it. After that, we apply the convolutional neural networks, okay, to classify a different stage of the lung nodules. So first, the pre-processing, we just simply to chop, okay, the noodles. After that, because we can see that each CT image, okay, we may have different size. So for the another pre-processing, we need to resize it to be the same size for the process. So there's some samples, okay, of the lung nodules in a different stage. Now, I would like to introduce one advanced CNN architecture. It's called the multi-layers convolutional neural networks. Unlike the conventional single layers, for the multi-layers, okay, we will have different parameters for each layer. For example, we have this convolution kernel. The filter size is 3 times 3. The second one is 5 times 5, and the last one is 7 times 7. So the advantage by using this architecture is we are able, okay, each layer we are able to, okay, attract the different features of the image. For example, this layer maybe can attract the features of the boundary. Okay, this layer may be able to attract the feature of the lung nodules for some detailed features, and this layer may be for another features. If we only using the single layers, we may lose some important information to help to classify. Okay, and then okay, so we can have how to combine each layer together. So we have this concatenated layer, okay, to apply some drop outs. Drop out is mean that how many percent of the output will fit into this layer. Because sometimes we have repeat a multi-layer, okay? For example, in here, we have 3 layers. So we may not use all the output, okay? Then we may just use some of the output vectors to be the single output to fit into the fully connected layers. It is because some parameter may be redundant to affect the classification performance. Okay, and then there's some results, some architectures, some level configuration. So as mentioned before, okay, we have the 3 levels. So we can have different filter size with different feature maps. So we have different parameters for each levels. Okay, there's some example to show what's the features, okay, for each layer. And then we have this experiment and results. Okay, we can show that based on this results. If we only use a single CNN, single level, the accuracy is only 80%. However, After introduce the multi-level CNNs, for example, three-level CNN, okay, the accuracy can significantly improve to 84%. So there's some different values of the dropout parameters. Okay, for example, if we use the drop-off equals to 1.0, that means all the outputs of each layer, okay, will fit into the 54 new levels. So the accuracy is only 75%. It is because there may be many redundant output. If we set that this parameter 0 to equals to 0.4, okay, then the value, the accuracy is increased to 84%. 0.4 means we only keep 40% of the output for each CNN layers. Then we can generate better performance. So finally, to compare with the CNN with a single level one, so our work is to generate the accuracy is 84%, while the conventional single layer CNN is only 62%. So this result is show the testing result for each class, benign, indeterminate, and minigrade. So this is all around 84 to 85%. Okay, for the second application is 3D ultrasound circular measurements. Scoliosis, okay, is related to the latent curvatures of the spinal. Okay, it's for the lomos laterals, okay, the angle should be 0 degree. However, for the scoliosis, so we have the bend, okay, it's greater than 10 degrees. So the golden method, okay, to attract the image, okay, to for further assessment is X-ray. So usually for the patient with the scoliosis, we use the X-ray image to do the assessment. However, the X-ray is well known. It is that we have the radiation. It's a radiation. We can increase the cancer risk. So we have another option, okay, using the MRI. However, the MRI, we know that it is radiation-free and produce a high resolution spine image. However, it is very expensive and the process is time-consuming. So that means it's not effective. Then we have another medical imaging method. It is ultrasound. So ultrasound is radiation-free, cost-effective, and most important, it is real time. However, the ultrasound, okay, the qualities compared with the X-ray and MRI is low. So that's why in this research, okay, we try to how to enhance the qualities of the ultrasound image and see how to find the features based on the ultrasound image to do the scoliosis assessments. So there's some overview of our ultrasound scoliosis measurement system. So firstly, we have this 3D spinal image. Then we use the VPR technologies to generate a set of the 2D projection image. After we have a set of the 2D image, then we have this ultrasound image quality selection using convolutional ranking networks to select the high quality image to undergo the further process. Once we have a set of the high quality projection image, then we have the some key process. It's called the bony feature segmentation. So in this bony feature segmentation, we will use the ULEX. So after this process, some bony features will be attracted. Then we can use these features, okay, used to measure the crop angles. Okay, so we have this, for example, we have this original ultrasound image, okay, with different angles. So we will use the deep learning to try to attract the features of the lower and upper wrist in the ultrasound image, look like this. So when we have the, So when we have all the features, okay, can be segmented. Then we can base on these segmented features to find the slope. So this is one of the examples. When we have all the features, so we can find the slope, okay, for each pair of the features, body features, then we can able to find the curve angles. So in this seminar, okay, I will introduce how to segment the bony features using deep learning. So by design, convolutional neural architecture is not capable to segment the bony feature in an ultrasound spine image. And also, there are two main challenges to be addressed while segment bony feature using CNN. So the first is choosing the kernel size of convolutional operation, which can handle the large variation in the location, shape, and size of the bony features. This is the first challenge. And the second challenge is the division and super architectures, which can reduce the symmetric gap between the encoder and decoder size. So looking at one of the conventional UNet architecture, okay, I introduced before. Okay, they have the symmetric gaps between the encoder and decoder size. So this challenge will affect the segmentation performance. So with this, we introduce a new type of the UNet. We call it the skip pathway inception UNet. In here, we call it seamless. So this seamless is the new method to do the biomedical segmentation. So in this seamless models, which contain the improved equation blocks and the redecided dense skip correction and the down sample path and the up sample path. As mentioned before, we have the first challenge. Okay, the first challenge is we need to see how to choose the kernel size of the convolutional operation, which can handle the large variation in the location, shape, and size of the bony features. So to solve these problems, we use two concepts. Okay, by using the SIFLab we introduced. So the first concept is okay. That we introduce the inception modules to develop a sparse high-performance computations. So compared with the conventional UNets, we replace the convolutional layer with equation box to merge the features extracted from ultrasound spine image, learned from the different location, shapes, size, and angles of upper and lower width. The benefit of this kind of the architectures was that the equation modules increase the depth and width of the module without any increment in computational requirements. And then the second concept, okay, we introduced okay the inception version 2. Okay, this is mentioned in lectures. So by using this inception box for our architectures, the series, so we try our module with replacing the convolution layers with equation layer box so that the features from image of different scale can be merged. Well, to solve the second challenge, to see how to reduce the symmetric gaps between the encoder and decoder size. So in the basic unit modules, the information gets lost during the maximum pooling and deconvolution operations. To retain some of the lost information, a skip correction are introduced to reduce the symmetric gaps between the encoder and decoder path. Here, the feature is coming from the encoders are supposed to be lower levels features, as they are computed in the early layer of the networks. So obviously, the decoder features are supposed to be at much more higher levels, since they are computed at the very deep layers of the networks. This results in a possible symmetric gap between the two sets of the features while they are being merged. So this is the our proposed seal nest. So in this seal nest, okay, we can see it is we use the encryption, okay, networks instead of the okay, yeah, in the instead of the convolutional layers. So it is a basic architecture of the seal nest. So in this seal nest, I'm compared with the conventional units. So we introduce, okay, we decided skip pathway. So by introducing the skip pathways, then we can improve, okay, the segmentation performance. So now I give some ideas, okay, how's the performance by using the seal nest compared with the different units methods. So we use this different matrix to represent the performance of the segmentation. So we use the Jacob index and the disk coefficients. So we compare with the conventional units and the multi-rest units. So multi-rest units is the state-of-the-art units methods, which is published in 2020 in this year. So compare with the different methods, we have a better Jacob index and disk coefficients to demonstrate we have a strong performance for the segmentation. Also, there's some examples. So for this example, we have this raw image and the ground truth. So by using unit, we can see that in the lower ribs, the unit, okay, is unable to segment. So we can see there's some overlap, okay, in these two ribs. However, by using the seal nest, you have a better performance. If this another examples. So actually, in the lower rib, we have 6 individual lower rib. However, by using the unit, the conventional one, it only can segment 1, 2, 3, 4, 5 ribs because there's some one is separate. But however, using the seal nest, we are able to solve this problem. Yeah, and then you can see that there's some seal nest is able to identify the upper ribs. Even there's some which is difficult to observe. However, the unit is unable to solve these problems. Similarly, the seal nest is also able to detect the edge of the upper rib like this. However, by using the unit or multi-rest unit, so it's joined together. And finally, the seal nest is also outperforms some state-of-the-art multi-rest units. For example, okay, actually, yes, there's 2 bony features need to be separate. However, the multi-rest unit is unable to segment. And finally, the seal nest is able to distinguish the both upper and lower rib clearly. Okay, thank you for your attention. Is any question?
Yes.
Yeah.
Yes. Okay, thank you very much, Dr. Steve.
Yeah.
There is one question, I think, in the Zoom chat, and I want to read that for you. Yeah. So this question is from Mr. Eka, and this question is, what if we extract the pitch? I don't know the pitch, yeah. Then use the principal component analysis in terms of reducing the dimension that then use double N after that. Is it still might be better to use CNN? That's the first question. The second question is, in general, what should be considered to choose CNN or NN? Or that are 2 questions for you, Doctor.
Okay.
Okay. Now you can answer the questions.
Okay. Yeah.
Okay.
Okay. So the question. Okay. So if you the first question is can we use the PCA, okay, to reduce the dimension using the neural network after that? I don't think so, because the PCA is mainly to find the significant input. okay, is not handle the image because the PCA is unable to attract the features of the image. So that's why CNN is more powerful, okay, used to handle the image rather than the new levels. Because even you use the PCA, you just try to reduce the dimension of some input parameters, but not the image, because the PCA is unable to looking for the whole image. But by using the CNN, the feature is based on the whole image to attract. In the yeah, so in to attract the image. So now we can see most of the researcher, okay, is use the CNN. No one will use the new level to attract the features. Even there's some simple image to classify. So that's why in some future West, so especially in the biomedical research areas. So conventionally, for example, so some signal processing, okay, to want to classify the ECG or EEG signals. Conventionally, they will use some signal processing to extract the feature first, like wavelet transformation to extract the features, then using the PCA, okay, to identify some significant features, then use some machine learning to classify. That is the conventional methods. But nowadays, in the last 2-3 years, so many researchers is moved to using the CNN. That means they are trying to use the image, okay, to represent the ECG or EEG or another biomedical signals. Then we can think how to use the image to represent all the signals. Then we use the image to fit to the CNN to classify. So that is the new direction for biosignal processing. It is because by using conventional feature adjustment method, like the wavelet or FFT, it still lost some important information. However, by using the image to represent all the biosignals, then most likely we can contain most of the important information. So with this, the performance will be better by using conventional feature extraction signal processing methods. Yeah.
Okay, thank you very much, Dr. Steve. Great presentations, ladies and gentlemen, have been delivered by Dr. Steve. Dr. Steve have introduced a fundamental and advanced concept of the deep learning method and how to apply this concept to various biomedical applications such as computer interface, lung cancer, and segmentation of ultrasound imaging. I think the last picture you saw to us, yeah, you can make that picture became clearer, yeah, became clearer. I guess. Okay, I hope this talk is very useful for us and can trigger maybe further collaboration between you and maybe us. And finally, thank you very much, Dr. Steve. Thank you very much. Thank you very much. And time is back to Mr. Master Ceremony. Okay, thank you very much for all. Thank you very much, Dr. Steve. And also
welcome.
Very much, Professor Khairul. Okay, time is back to Mr. MC.
Thank you, Dr. Ahmad Marzuki, for being the moderator for the first session of the session. We will now continue to the second session of the plenary lecture with our moderator, Dr. Risa Suryana, an associate professor from Physics Department, Universitas 11 Maret. Please welcome Dr. Risa Suryana.
Okay. Thank you, Safira. Okay, Bapak dan Ibu, ladies and gentlemen, welcome to the second plenary sessions. In this seasons, we have two scholars. Actually, yeah, the first presenters, Prof. Budi Purnama, and the next presenters, Prof. Didi Pascal. So I think Prof. Didir will join about 11:15 in Indonesia times because the times Paris is 5 hours behind of Solo. So at 11:15 minutes we'll join in this second plenary session. Okay, ladies and gentlemen, yeah, we have two scholars who will share the expertise. The first one is Prof. Budi Purnama, and then the second presenter is Prof. Didi Pasquale. We have 1 hour 30 minutes, so I will share about 45 for each presenters. The first presenter, Prof. Budi Purnama, I will give you 30 minutes for presentations, and then 15 minutes for the question and answers. So Prof. Budi Purnama, just inform to all participants, this is the new professors in our department, Physics Department, Faculty of Mathematics and Natural Sciences, Universitas 11 Maret. He is the fourth professor in our department. Prof. Budi Purnama will present by title Control of Nanoparticle Size in Cobalt Ferrite Systems. So please welcome. It is time to give this time 30 minutes for presentations. Prof. Budi Purnama, please.
Okay, thank you very much, Mr. Risa Suryana. Can you see my slide? It's okay. Okay. Thank you very much for the challenge in this moment. I would like to introduce myself. My name is Budi Purnama. I come from Physics Department, Universitas 11 Maret. In this challenge, I would like to talk about control of nanoparticle size in cobalt ferrite system. And the outline of our talk is about like this one. The first is introduction regarding the cobalt ferrite nanoparticle magnetic. We abbreviation NPM, nanoparticle magnetic. The second is the experimental. The third and other, we will discuss about the result of the effect of annealing time on cobalt ferrite nanoparticle magnetic. And the fourth, synthesis temperature effect, calcination temperature effect, and we also the effect of cation metal substitution. In this case, I would like to set the aluminum for 30 and strontium, and we get conclusion for the next work. A big discussion about the magnetic material. When we downsize material, we downsize like we have some hard disk, HDD, or we have CD compact disk. So there is some material we downsize by lithography technique, or maybe we have some nanoparticle synthesis, nanoparticle magnetic. We carried out by the ball milling synthesis or by chemically synthesis, we get the nanoparticle. So the material when the very large size is magnetic, but after we downsize become very small by lithography techniques or in natural nanoparticle synthesis, we get the superparametric limit. What is superparametric limits? This situation when the magnetic loss in the material. The superparametric will contribute on two parameters. One is single domain on and a divine pattern on individual particle. This is the limit. There is one parameter is blocking temperature. Later we discuss about blocking temperature. In theoretical science for single domain realization for single domain, we can calculate by this formula. There is some stiffness constant, anisotropic constant, and also saturated magnetization in here. By using the formula, we can get in theoretical magnitude the single domain realization we can realize when the sample less than 100 nanometer. However, the experiment report that the nanoparticle realized in single domain realized when sample size less than 30 nanometer or the recently 45 nanometer. And this one is case for cobalt ferrite nanoparticle. Okay, the next, why cobalt ferrite nanoparticle? Because the material owing high magnetization saturation. We have some material high saturation magnetization. We can pattern become very small. And also high coercive field. This is also same the previous case. Some material have high coercive field, so we downsize, so they cannot lose the magnetic parameter. And also chemical stability realized, and of course realized in single domain below blocking temperature. So that the exciting property opportunities applied in several applications. For example, in recording medium or in contrast agent for magnetic resonance imaging and photocatalytic agent antibacterial, as well as early cancer diagnosis and targeted therapy procedures. So this is very interesting and application regime. We can see in this feature that why single domain become magnetized in other state in here. This is the initial state, and other is the switching state of other switching state. This condition to another switching condition, there is some energy barrier. The time required from this position in this is time relaxation. By time relaxation. However, in case nanoparticle magnetic, the time relaxation correspond to blocking temperature, that the material is still owing magnetic characteristic, magnetic properties. But we have some material magnetic, and we have some material divide become two. So this is magnetic and magnetic. And divide two again, so become 4 magnetic until the divide become nanometer order. So there is some limit. So there is lose the magnetic properties. This is when blocking the temperature. So the related the magnetic state is still realized. And the other particle size is correspond to magnetic saturation. So the reciprocal requirement, how the magnetic saturation and blocking temperature, we can get the superparametric condition or in single domain configuration. So in this our talk, we will review some temperature synthesis dependent on the cobalt ferrite nanoparticle, and also the annealing time is the second one. So we have some time. We also discuss about synthesis temperature and also calcination temperature and aluminum or strontium substitute in cobalt ferrite system. Okay, this is the experimental. In our experimental, we have carried out in semi-clay road by co-precipitation. Maybe this is in the most important one because this is carried out in not high, not usual lab we can carry out this process. We have some material such as ferronitrate, ferrinitrate, cobalt nitrate, like this one. We have some solution in here, some more, and some stoichiometry molar in here. So we can drop bias in natrium oxide, dioxide, and we get some precursor in here. Just be washed by the deionized water, or we can acetone or etc. We can wash again with water, deionized water. After that, we overnight heating. This is some literature 100 degrees. So we can other choice. We can get a synthesis sample. A synthesis sample can carry process another pressure like this one and annealing. So we get some sample nanoparticle cobalt ferrite. This is our standard characterization FTR, RD, and VSM. Some is additional. Okay, we get the first data we can share here. How about effect of temperature synthesis? In this review case, after this one, this is the only we carried out at room temperature. After that, we get sample as final sample. But the red one, after we get the room temperature, but we synthesis not at room temperature and temperature near boiling water, 19.5 degrees C. So we get that one. This is the FTR result, very different. So we can option the XRD sample. There is no difference. The two data big diffraction. So there is maybe there is some material, and we confirm this is the same material, but different broadly in the strongest peak here. This is indicate the crystalline size. And this one, in the red one, when we carried out at room temperature only, the very small crystalline size is realized. But when we carried out in very high temperature, 95 degrees C, following 600 degrees C for our annealing, we get crystalline size around 37.9. This one. For comparison, other researchers also reported and carried out at 40 degrees C. We get the 7.4 nano crystalline. So, what kind of different crystalline, different microstructure and magnetic structure? This is the visual of VSM image, typical visual image. When carried out at room temperature, there is some hole realized in here, but this is compact. But the important is not here. We can confirm here that magnetic properties is different by the different microstructure. This is the fundamental in here. So this is very nice VSM and red one, and not so good and black one in here. Okay, we can. The next is the annealing time effect. How about the annealing time effect? And here, after the sample is obtained, the next procedure post annealing at room number 8, annealing at 60 and 60 degrees C for 2, 6, and 11 hours. So we get result in this. This is the FTIR profile by different annealing time. We get data like this one, but there is no the corresponding to wave number is narrow. There is no almost same in here, almost same in here. So there is maybe this the metal oxide relation same. We also confirm by XRD by the 2 hour, 6 hour, and 11 hour. From this result, we can calculate the crystalline size and the strongest peak, 3-point orientation. Can get almost same, 21.4 nanometer, 21.6, and 21.7 nanometer for different. What different by following the annealing? So we proceed another characterization by this one. This is the same image on the result. From this result, we also get some information. This is the typically nanoparticle ferrite. There is no difference. But however, how about if we calculate the average grain size? So we constant one circle in here is nanoparticle. So we can make some size distribution like this one. So after we get some numerical calculation, we get a result. A Gaussian narrow distribution is obtained like this one. When the sample carried out in 2 hour annealing temperature, the distribution of around 12.5 nanometer until 75 nanometer. But when very long hour annealing temperature, the distribution become narrow because the distribution from 20 nanometer until 65 nanometer. How about the chain distribution regarding the magnetic properties? We can get this sample. So from this PSM result, we can get the magnetic saturation 110.5 mMo per cc, and by annealing become enhanced, become 140.5 mMo per cc, become magnetic saturation become enhanced in here. But the important point in here, but the magnetic property of cobalt ferrite nanoparticle is confirmed dependent to modified crystalline size. This is the fundamental in our case. Yeah, this is this one. Coercive field also this one. The coercive is little bit different because there is a different distribution of this one. This is another result. How about synthesis temperature effect following annealing at some elevated temperature? In this one, we choose 1000 degrees C for annealing. This is the FTIR results. Yeah, FTIR. This is we carried out at 40 and 5 degrees C, 80 and 5 degrees C, and 90 degrees C. The absorption position and there is not different for each another. So by annealing, by synthesis, by different synthesis temperature, we can expect that the same sample is obtained here. After that, we confirm by the XRD, this one. So by the different synthesis temperature, like this one. From the some review paper, we can obtain the cation distribution in case cobalt ferrite in spinel structure. The cation distributed in octahedral site and tetrahedral site. So following the result, we can obtain, we can calculate the ratio of 1222 over 1220 in this, the distribution and octahedral site, and also intensity and 222 over 1422, this one, and this one. So we can get the cation distribution. By following the result, we can obtain 4 different synthesis temperature. When we calculate an octahedral distribution, tetrahedral distribution, we get magnitude like this one, 3.43, 3.4, and 3.48, and calculation for theoretical around 3. So there is almost same in this case. Different for other case, intensity is 22 over 422. This is 1.68, 1.52, and 1.24. Theoretical close to 1. From this result, so the octahedral site may be distribution cation is oxide occur in this octahedral site. We can expect that the octahedral site is there is some distribution cation. This is the same image. Okay, like this one. This one, very nice, and other. Usually, different morphological will change the coercivity magnetic. So we can form here. By changing the morphological shape of the nanoparticle in here, we can clarify that coercivity also different, become increase in here. This is 60 around 64, 25, 9, 23 in here, become 9. How about the saturation magnetization? Saturation we can calculate by the distribution cation in octahedral site subtracted by tetrahedral site. Yeah. By the calculation, magnetic saturation is become decreased by increasing synthesis temperature in this case. So that we can get from this formula, we can expect that the octahedral, there is some octahedral site that become redistribution. So the total of magnetic saturation become decreased by increasing annealing temperature. This is other result about the calcination temperature effect. Yeah. This is the first feature is the TGDTR image. This is the weight loss of our sample. This is realistic. After about 500, around 500 or more, the sample may be stable in here. So there is some energy from annealing will use to increase the crystalline quality. Okay, this is the X-ray diffraction pattern for cobalt fluoride nanoparticle at different calcination temperature and 600, 800, and 1000 degrees C for 6 hours. From this result, we, as in the previous, like the previous result, we can the crystalline size and the strongest peak in here. We can see in here the crystalline size tend to increase by increasing calcination temperature. And like this parameter, there is no difference. So this is good. So there is no different sample, or the structure is stable in here. How about the distribution cation in here? Wow, this is difficult to get information from this ratio because there is no tendency by the increasing temperature calcination, how the increase or decrease there is no. So they expected that the cation distribution may be occur in both octahedral and tetrahedral side. Okay, what different? When the annealing calcination temperature, what different the morphological? There is some different morphological surface morphological occur in here. This is 600, this is 800, and this is 1000. This one, 1000. And we can also calculate the particle size distribution in here, insert and here. But from the image, we can see clearly that for the 1000 degrees C, the morphological is different. This is some compact granular. This is like one or more nanoparticles spiritly. This is one is nanoparticle spiritly, is another. But for 1000 calcination, there is some other phase. Maybe we can call compact structure in here. So we can this one. So the difference is the morphological will change the magnetic characterization here. So we expected that Fa3 plus terminally migrate to octahedral side with the increase of calcination temperature. This is we can YMS become increased by this one. So and we could regarding why in the morphological we can discuss like this. John that. And also we can confirm coercive field depend on particle size. And this we can see in here. Coercive field also, but very difficult in here. From 600 degrees and itu become increase, but in 1000 is decrease. The different morphological we can relate the condition. Okay, this is another effect of aluminum substitution in covalent system. In this left one is we modify the content of aluminum and the cobalt ferrite nanoparticle from 0, 0.01, 0.1. After we get the sample, we following annealing at 600 degrees C for 5 hours. At the sample, we select one modified composition 0.1 and we foreign the annealing.
Pak Budi, you have 5 minutes.
Okay, thank you. So the different aluminum is there is no the absorption position, there's no difference. This is also same. So there is no modification structure in here. Maybe metal oxide. How about the SRD pattern? Also same the previous result. So this is the structure is very stable. This is we can call the substitute aluminum in cobalt ferrite. So aluminum substitute the crystalline structure of cobalt ferrite. Crystalline side increase by increasing aluminum, and density decrease due to the substitution Fa by increase also. The crystal. This is other result by annealing temperature. Yeah. And this one, crystalline size decrease by increasing, and density become decrease because redistribution cation and octahedral side. About the PSM result, okay, this one. This is very clear. This is clear, I see. I think by increasing aluminum content in magnetic matrix, so the saturated matrix become decreased. This is logic. How about the annealing temperature increase? The increasing saturation. So we can call the redistribution cation octahedral may contribute the increasing of the matrix. This is the complicated result from our result. We can collect this one. How about the temperature and ask for all our sample? And this is the all our sample. Okay. Also in coercive field and monetization. For this is maybe clearly by increasing annealing, so magnetic saturation become so redistribution cation octahedral is clearly occur in this one. And coercive field, this is depend on the morphological characteristic of the sample. Okay, this is the other. In the previous case, we choose aluminum because three cation, but in this 2 cation, strontium is 2 plus in here substitution. And we can annealing and like an relative low annealing. If we see in the strongest peak, we can enlarge in the right position. So the strongest peak tend to shift and shift to left to the strongest peak. How crystal microstructure change in here? We can calculate. How about the crystallite size? How about the lattice parameter, density parameter, and lattice parameter? By the annealing, we can get the crystallite size increase by increasing. This is the usual and annealing procedure. This is same. This is the FTER. So we can discuss in here. An increase in annealing temperature lead to increase in crystallite size and the lattice strength decrease with the increase in crystallite size. This result is consistent the previous result. And what this is the crystallite size increase. How about this is around 36%, and the lattice strength become this one because the strength crystalline also change the magnetic properties. So we can calculate this is significant or not in magnetic properties. This is the typically of the FTER of the cobalt ferrite. So what about the magnetic properties? Yes, the magnetization, there is some increase by increasing annealing temperature. This is some redistribution cation octahedral. How about the coercive field? This is complicated. This is complicated. But the first expression does there is some morphology is different, so the magnetic coercive also depend on magnetic coercive. But if we discuss about the single domain configuration, the large coercive field is indicate the single domain configuration is realized. So we can. So this is maybe maybe at the 400 degrees C, the single domain configuration is realized. But by the increasing the sum morphological become reduced the coercive field and also in this position. Unfortunately, we cannot measure the blocking temperature because this is unavailable in Indonesia. The interesting the lattice parameter increase and density are not sensitive to change in crystallite. This is the point. Okay, this is the final our talk and conclusion. In the previous discussion, we can control nanoparticle or we control of nanoparticle size and cobalt system. We discuss some parameters such kind temperature synthesis, time annealing temperature, calcination temperature have confirmed modifying the structure and magnetic properties. The ease of tuning of design properties will promote the for design application. So what open the possibility we can create in our lab? One is photocatalytic absorber material for removable dyes. This one possibility we can carry out in our lab, and also the antibacterial material. Okay, this is our talk. Thank you very much.
Okay, thank you, Pak Budi. Okay, ladies and gentlemen, the time is the question and answers. So participants can deliver questions through write in a chat column, or please give a thumb at this time or clap. So in our committee, we'll open your audio. Please, ladies and gentlemen, Pak dan Ibu. Okay, any question? So we have about 9 minutes for question and answers. Okay, Pak Budi, I have questions. So in the previous your slide, you mentioned that applications of global ferry system to apply it, for example, hard disk and also solid state devices. So I imagine to apply this material to make like thin film, right? Not because
yes.
your sample is like powder like.
Powder like, yes.
So, but in the reality, to make hard disk or solid state devices, we have to make a coating on the substrate.
Yeah.
So how about that?
Yes, there is some two dimension, two type of cobalt ferrite. One is cobalt ferrite bulk cobalt ferrite. This is the typically we have some maybe thin film produced. We have some target by cobalt ferrite target. So this is the bulk we in bulk dimension. But this is another in powder like. So if we have some powder bulk light, we have some maybe an evaporator system. We can evaporate the bulk cobalt ferrite, so we get the film. After that, we get photolithography. We patterning and downsize by photolithography, and so we get some track or maybe some pattern. So this is become similar to what can we shoot downsize until. So this is the superparametric limitation. And nanoparticle one is maybe suitable for contrast agent, for magnetic resonance imaging, photocatalytic agent, and antibacterial maybe. Okay, I hope it's according to your question.
So because yeah, I cannot imagine because your samples powder samples to apply for example recording mediums.
Yeah. Yes, from powder like we can compress become bulk sample.
I think this is not easy to compress.
Yeah. I see. Yeah, this is different procedure, I think. And yeah, after we get the bulk material, so we can use the bulk material as source for thin film target in sputtering or in evaporation system. by
molecular
by sputtering system or by evaporation system, we can evaporate this sample cobalt fluoride, so we can get the film. So maybe the thickness around less than 100 nanometer. After that, if we want to use as the HDD, so the film should patterning down size and one maybe in chip very small, maybe now in 100 degrees, 100 nanometer or less than that, by lithography technique or maybe other technique, photography. But the limitation of the hard disk should also regarding the supermagnetic limit. What the size of the small patterning should close related this equation. So yeah, maybe if we patterning in 1 micron or 50 micron time 50 micron is okay, no problem. But it's smaller than 1, maybe we should regarding the superparamagnetic limit.
Okay. Thank you, Pak Budi. Okay, ladies and gentlemen, any questions? We have only 5 minutes. Please. Okay, Pak Budi, I just make clearly, but because you said about crystallite sites, you mean crystallite site means only one orientations, right? Because I think you use Scarrer's formula, only 311 orientation.
Yes, 311 orientation. I calculate the crystallite size, but we have some another people reference. Other people we can also William Bloch. Also we get some result, but from there is some reference. There is some calculated by average for 3 peak XRD. Another by using one single strongest peak, another William Bloch plot, the all peak is used in that. So the final result is not so different much. So in our case, so we select the strongest peak in our study.
So in your research makes modified our particle size and using calcination temperature and also doping aluminum and strontium.
Yes.
So, generally, the structure is almost similar. Right?
Yes, almost similar.
Data.
Yes.
Okay, Bapak dan Ibu, ladies and gentlemen, please. Yeah, because limited time. Yeah, almost finished, I think. Just 1 minute left. So thank you, Pak Budi, for interesting presentation. Okay, thank you.
Thank you very much, Matur nuwun.
Okay, the next presenter is Prof. Didier Pascal. I think Pak Didier Pascal already here in Zoom. Prof. Didier, could you hear me?
Yes.
Okay. Okay,
Yes,
good morning.
I'm hearing you. Yes, very well.
Okay. Good morning in Paris time.
Good morning. Yes, selamat pagi.
Selamat pagi. Okay, Prof. Didier, we have 45 minutes. So we can share, so we can divide the times, 30 minutes for presentation and 15 minutes for question and answers. So ladies and gentlemen, Prof. Didier Pascal from University du Littoral Côte d'Opale, France. He will deliver research with titles Improvement of Functional Light Properties for Applications. Prof. Didier, time is yours at 30 minutes for presentation, please.
Okay. Yes, I guess that now you can see my presentation.
Yes. Yes.
Okay, perfect. So today I'm gonna talk about, the improvement of functional oxide properties for applications. So this is some results of different collaboration I have with, after my name here, you can see three PhD students and some colleagues. Some of them here are from Morocco, because I started a collaboration, 2 years ago with them, and I'm gonna talk about some results about that. Finally, yes, just to look on France. We are located, in the north of France, here where you can see Rico, and we are 300 kilometers far from Paris. So I will have an introduction about finally this famous functional oxides. I'm going to talk about three different parts. That means three different kinds of results. First part will be on ICT ceramics dedicated to high-Q capacitors. Second part will be the composite material for electricity storage. And the third part will be a new part on finally how to predict some results by using the density functional theory. And we'll see an example about the study of BSN. And finally, I will conclude on every part of my presentation. So what is functional oxide? Well, what can we call functional oxides? That means oxides which have some interesting functionalities. Like some of them, I can speak about some. High dielectric permittivity, piezoelectricity, pyroelectricity, and photoelectricity, and that means many other, properties. And that also means we can do a lot of things with oxides applications, such as, ceramic capacitors, tunable devices, actuators, sonars, sensors, memories, and so on. And these materials, have a lot of properties. And of course, we have an interaction between physical properties and all other properties. And for these other properties, we have some electrical, mechanical, and thermal properties. Leading to, other properties like dielectric, piezoelectric, and so on, electrocaloric, converse, piezoelectric, piezocaloric, thermal expansion, so lots of things. That means a lot of properties possible to study. And I guess since, not more than 15 years, our community attention was attracted by other properties and materials like, high temperature, superconductivity, colossal magneto resistance, multifluidics, gas sensing, thermoelectrics, oxide for electricity generation, and for the main application, we can find fuel cells and solar cells. And of course, we have also the energy storage, because when you can produce electricity, it's also very interesting to store it. And so finally, for functional oxide, we have some special oxides exhibiting phase transition in strongly correlated electron systems. For me, I'm specialized, in the study of a special structure, and this structure is called perovskite, a well-known perovskite structure. Identified as a simple formula to AbO3. And in every oxide, you have a special structure with grain boundaries, impurities, and structural defects. And finally, between these grains, you have boundaries. And for each grain, each grain is not perfect, so you have inside, you know, in this composition impurities, and about this physical structure, you have also structural defects. And all these, finally, was this intrinsic and extrinsic properties will have a strong influence, you know, on the dynamics of this ferroelectric central domain. So, everyone, you know, is now, you know, about this famous structure. A simple structure for perovskite structure with, you know, the main ions in the corner, and finally the other ions in the center of this cubic, pseudo-cubic structure. And we have here a third of oxygen. That means we have, you know, a system. We can call it, you know, correlated electron system, because, of course, all ion will be ionized, you know, by electron or, of course, positive charge. And we have here, you know, a view of this system where we have some positive charge here for barium, you know, and titanium, and of course, all oxygen, you know, are charged with electrons. What is interesting to remind to everyone is also this system, this oxide will present different phases in function of the temperature. Here you have an example for PT. PT, we can, you know, shift from different structures, I mean different crystalline phases, from, you know, minus 90 Celsius degree to 120 Celsius degree. And of course, you can also tune, finally, this shift between the different phases, not only, you know, by moving the temperature, because you can tune, finally, the different phases by modifying the composition. I mean, by doping, finally, the initial structure. For this simple example, if you have your BT, you can dope it with different kind of dopant to exchange one or two ions in the structure, in the unit cell. And with this exchange, you know, of ions, you will also tune, finally, the phase. That means it's very so interesting, because if you want to modify the properties at room temperature, you don't have to move temperature. You can just, you know, tune the composition. So the dynamics of these defects, so the defects you can have in your structure, because of course, finally, you have an idea with a perfect structure, but in reality, of course, the oxide is composed of different, you know, proposition of different cells. And the cells and the structure, finally the grains, are not perfect. So you will have some local electric fields, domain boundaries, surfaces, chemical potentials, and the different parts, you know, will influence by ferroelectric and ferroelectric domains. That means that you will have an interest in ferroelectric and ferroelectric properties. And for some application, you will also have an interest in the catalytic action, because you will have some special, you know, interaction as a surface of your oxide. And we will talk about catalytic action. That will be also very interesting, of course, for sensors. For this shifting between different phases, here is a simple, you know, figure where you can see a transition between the ferroelectric phase to the ferroelectric phase. For every kind of oxide, it's not only for BT. State, of course, you will have some special properties like piezoelectric, bioelectric, and ferroelectric application. And above, you know, temperature, degree temperature, you will stay in the cubic phase. In this stage, you don't have, you know, any spontaneous polarization. So you will also have an interest in this ferroelectric state, because it's also very interesting when you are developing, you know, some components for radio frequency application or microwaves. So here, on this slide, you can see all properties, from finally the prediction you can do, on your material to the final application. And in every step, of course, you have all the scale, that you can, where you can study, your material from the unit cell, to grains, where you can have your domains, where you can see a different grains if you're ceramic. After that, of course, you can deposit the material on substrates, and we are studying at this time films. And then if you integrate them into components, you have a final component. And it's a different length of scales. You can study different things between the atomic scale to the device. That means, of course, in our interest, we have many things to do. And we can study from the composition to the response of different signals and different constraints. And finally, for scientists, we have many things to do because we'll be able to do the correlation between the structure and the property of the structure to the microstructures, the processing, the architecture and performance of the device, and so on. So today I will discuss about different scale. Of course, I will present something about, the ab initio calculation. That means you predict the behavior of your material. After that, I will also present a study of a ceramic, special ceramic dedicated to application. And also, I will also predict, also talk about, flexible material for application. Some of my applications are related to energy storage. In this fragment plot, you have an interesting view about how to compare finally the different devices between, the conventional capacitors, I mean electrostatic capacitors, supercapacitors, and batteries. And of course, the most well-known of these batteries are today, Allianz battery, because lithium, is very used today in the development of batteries. But this is batteries which are currently applied, in automotive application and so on. And every device we have in our phones, we have this kind of battery. So now researchers are developing all new materials for these three kinds of applications, from conventional capacitors to batteries. And if you have a look, of course, we have an interest in every kind of application, because battery, okay, it's very interesting, because you have the highest energy density, but for electronic application, you have an interest in developing, capacitors, I mean electrostatic capacitors, because in this conventional capacitors, you have the highest power density. And of course, you don't have to mix these two properties between power density and energy density. So to characterize, finally, a material dedicated to energy storage, you will have to study different properties. At first, I will come to these properties later. You will study the dielectric properties, but also the photoelectric properties, because for the calculation, of the different energy density, you will have to study, the photoelectric properties. That means you will measure, the ferroelectric cycle, where you can see the evolution, like this example of the polarization and function of the electric field. And what I've done, on this simple figure is to present finally different area. You have here in the center, of the cycle, you have the red part, which is the interesting for ferroelectric application and in memory, because for memory, you want to have the highest, random polarization, but for energy storage, that's not the same thing. That's finally the opposite case. When you want to store energy, you have interest in the green area, this one, because this one will is called, the recoverable, energy density. Here, and this simple figure, I present, the different kind of material you can study. You can have some usual dielectric. I mean, this is, you are always, like in a simple dielectric, you have behavior like the paralytic behavior. And if this is a presentation, sure, of the evolution of the polarization function of the electric field, the ferroelectric cycle, usual things. For relaxer, you have another kind of cycle, very thin, but if you see finally for relaxer, you have a very low random polarization. That means it's not interesting for electric application, but finally the other part here is related to the storage of energy, and here the surface, for the storage, energy storage is very high. That means that for energy storage, electrical energy storage, you have two kinds, of interesting material. Here, relaxer material and antiferroelectric material. Antiferroelectric, here, the last case, is very interesting because in this spatial behavior, you have a double cycle, That means here, the surface for the storage is the highest one. And I have a special interest. That means today, I have also a PhD student who is currently studying, STO, and I will talk about that later. For energy storage, finally you have to study a lot of things: the electric permittivities, the electric losses, the polarization, because you have interest in saturation and random polarization, as I said previously, and field, corrosive field, and maximum electric field. So now some application and some examples. Of course, I only, in my case, I choose, in the beginning of my career, I choose to study only, lead-free functional ceramics and lead-free materials, because in Europe we have special interest in that. In Europe we have the Roche directive. It's a European directive, which is where some pollutants are strictly forbidden for application, and lead is one of these highly pollutant. That means we have a special interest in lead-free functional ceramics for energy storage. Here I will present some results about SCT. That means you have a connection between strontium and calcium, and you have titanium. So how do we realize our materials? This is a Solvil, synthesis. This is a simple route, because I present here the usual way to do it. Of course, for strontium and calcium, we use acetates, and we dissolve it, in acid acetic. After that, we have our titanium isopropoxide also. So we mix finally the two solutions, solution of strontium calcium and solution of titanium isopropoxide. We dilute a little bit, with ethylene glycol, which is very interesting to stabilize, our solution. And after that, we have the solution. With the solution, for my personal interest and because I'm conducting a lot of study, because I have a group of PhD students, and I develop films, cell films by thin coating, deep coating, and sputtering. And here, with the solution, of course, you can use the spin coating or dip coating to deposit a film, on a substrate. But we also, transform finally the solution into a gel. This gel is dried and then, calcined, to obtain finally a crystalline phase. And after that, with this powder, of course, as everyone knows, you will pelletize it, to obtain some pellets, and that means ceramics. And these ceramics are sintered, at very high temperature, generally between, 1,300 to 1,400 degrees. For, the duration can be tuned, of course, when you study properties. For our, compositions, at first we studied physical composition because, of course, we have the reference. I mean, the STO without any exchange of by calcium. And after that, two composition with calcium, 0.35 and 0.4. This composition were chosen because we have a special interest in this composition because at this for this composition we have very low losses, and this is, if we study these materials, you can see that this material will not present, antiferroelectric properties for each composition. So it is impossible to have an extended doping. That means you focus on special compositions. So we have verified, of course, the phases, and our phases were pure, so that's very, very good. For STO, at room temperature, this is cubic structure because STO is paralectic in the paralectic state, at room temperature. For SCT, we are, we have an orthorhombic structure. Here you can have, you can see, the SCM photos of the material. Here is TO, SCT 0.35, and here SCT 0.4. So finally, we have an influence, of the composition and the grain size. So the grain size, increases, in function of the composition. And of course, the grain size, is influencing, of course, the electrical purposes. Grain size is very important parameters for, tuning the physical properties, but also for tuning, finally, the electrical properties. All, electrical properties will be tuned with the grain size. It's also a very important parameter. So here you can see the dielectric evolution in function of frequency. Here we have studied, in very extended range, from low frequency to high frequency. Here we have 1 gigahertz. So what we have observed finally, from the composition, here we have a STO, and after that you have the SCT. With SCT is very interesting because you have a flat curve. This flat curve is very interesting because it's meaning your properties are stable whatever the frequency. Here, on the right, you have the evolution of the loss tangent in function of frequency. And here, for us and for me, is very, very interesting. That's why now, today, we have a special focus, here, because what we can see, what we can say about, this area. You can remark, that we have an evolution here. So for the composition, for a city, you have a decrease, continuous decrease of the losses. So you can see the value. You are lower than 10 to the minus 3 to 10 to the minus 4. That means the losses are very, very low for this ceramic. And here, you don't have any points. You can see you don't have any measurement points. Why? It's just because the losses were so low that our impedance analyzer cannot measure. It was impossible for the equipment to measure the value of the loss tangent. That's very interesting for us and for our application. Our application is capacitors. So here, in this table, you have a comparison of the composition of the different material, STO, the reference, and our CT. And our lowest, loss tangent was, 210 to the minus 4. And it was a very low value. That means when you calculate this coefficient, this is the quality coefficient. The quality coefficient is calculated by the reverse, it's the reverse of the loss tangent. That means here we have a very high, quality factor. This quality factor is very, very interesting for the development of capacitors. Here is, of course, MLCC. MLCC means, a multi-layer ceramic capacitor. And for industrial application, the requirement is, the quality factor must be higher than 1000 up to 100 megahertz. You can see this special, feature, in technical documents about, the fabricant of capacitors. For the calculation of the density of the stored electrical energy, you have, of course, to study the ferroelectric behavior. That means this is the evolution of the polarization in function of the electric field. And here, for this composition of a CT, we have developed two kinds of material because we have realized the material by, here the solid-state reaction, solid-solid reaction. And a second route was studied, that was the solid route, because when you realize, your powder just before to make the pellets, by developing different, way to elaborate your powder, to make a powder between here, for example, solid-solid reaction and solid route, you will modify mainly, you will modify the grain size. The grain size and the distribution of the grains. And it's very different because for the solid reaction, you have an extended distribution of the grain size. But for the solid route, you have, a quite, a narrow, you have a thin distribution. That means, finally, the difference between the grain size is not so high with the solid route. And additionally, you have a smaller grain with the solid route. And we have compared here with ferroelectric measurement. We have calculated, the different energy. And what you can see, of course, here is we obtain finally a higher energy with the solid route. And it was very different because, you can see I've highlighted, the main properties here, the stored energy, and here the efficiency. That means this material can be, dedicated to ceramic capacitors. For this first part, I will conclude. SCT was very interesting, especially, this composition with 40%, of calcium, because we obtain a very high value of the quality factor, and very interesting for developing, MLCC. And we have, second parameters, we have shown, that finally the solvable route is more interesting for our study because we obtain the highest values with this route. Second part of my talk, is dedicated to composite material for electricity storage. And here, this is material, composite material based on PVDF. And we have started to study, with this PVDF alone. And then we have added, some ceramic particles into, the polymer matrix to modify, the properties. So why do we study this material? For the previous material, of course, you have ceramic. But ceramics, are not flexible. With PVDF, you obtain a flexible material. So flexible material are also very interesting because if you know, the structure of electrostatics capacitors, the technology for developing an electrostatic capacitors is interesting because you will roll, the different layers. And in this case, you want to roll, finally your material, you have to use, flexible materials. That's why here we studied, the PVDF. What is PVDF? This polyvinylidene, fluoride is a semi-crystalline polymer. So you can crystallize, this material in function of different route for the modification of the phase, because you have the main phase alpha, beta, and gamma, and you have also other phases. But the main ones, the more interesting ones, are alpha, beta, and gamma. And you will be able to modify and to tune finally the different phases by two ways. The first way is the temperature. The second way is the constraint. I mean the mechanical constraint. Here we have used the first way. So we have modified the temperature of crystallization to modify the phase. So how do we realize our film? Because here we are talking about thick films. We use spin coating technology. And of course, at first we make our solution, PVDF. After that, with our spin coater, we deposit our film, on glass substrate. And then we obtain our film. When in the last step, of course, we have to anneal our film at different temperature because we have studied, the different phases. And this is the film we have developed, because you can remove after. What is interesting when you deposit your film on glass substrate, after that you can remove the film and you obtain a flexible film and transparent and flexible film. So now I present, the physical characterization of our film with first the XRD, because with the XRD, we have here, you can see, you have the different temperature of crystallization, different parameters of crystallization for our films. That means that we observe a difference. Here, this is the lowest temperature in black, the black plot, and here the highest temperature. That means that first here, for the lower temperature, here we have only finally the gamma phase and beta phase. Here, beta phase, gamma phase. And for the highest temperature here at 130, 130 Celsius degree, we obtain the alpha phase. If you observe the film, with the SEM, you can see, the films, are homogeneous and with quite low roughness. So this is interesting, of course, for this kind of application, because you can, with spin coating, you can realize, a very huge sample. And in this way, it's very interesting to have on modern surface. Now the direct characterization of these films. The study was conducted in room temperature, and you can compare here this evolution of the PVDF for different, because at first, we have studied here the concentration of our solution. And for comparing our material, because I'm saying it here to every researcher, every time you work, you have to compare your results to what's possible to be compared. And here we have to compare our samples to our samples, here for the blue, red, and black curves to PVDF, commercial PVDF. Commercial PVDF is in green here. So the word curve. That means here we have obtained, here you have the electric constant in function of frequency. Here you have the loss tangent. What can we do with that? It was very interesting for us, because we observed that by tuning, finally the composition, I mean here the concentration, we have tuned, the value of the electric constant for, here for the composition, for the concentration of 0.3 gram per milliliter. We have obtained, the highest value of the dielectric constant. And for the loss tangent, it was also very interesting, because here, by comparison, of the commercial here, the commercial PVDF, we obtain lower losses in the range of frequency that is interesting for application. So the table, is given, the different values of the electric constant and loss tangent at 1 kilowatts. So for us, we finally, for the other part of study, because the first part, was dedicated to the study of the concentration of PVDF. That's why we choose, this concentration for our other studies. We have, of course, an interest in the storage of electricity. That means we have, studies of electric cycles to calculate, the polarization, and here the energy density. And for the different here, you have a study in function of the electric field. We have an evolution, of course, of the energy, because we have an evolution of the cycle. And we were very satisfied, of these studies, because, we obtained an energy density, of 1 joule per cube centimeter. It's a good value, for energy storage. Finally, for the composite thick film, we use the same technology, spin coating, but we have mixed, PVDF with particle of oxides. Here, the oxide we have choose to study and to use is BT, barium titanate. After we have our composite solution, of course, we have, by the same technique, we have realized, our film by deposition at first on a glass substrate, because I remind it, by depositing, on a glass substrate, in the latest part you can remove, you can peel the film from the substrate to obtain your flexible film. For our composite, here with XRD, we can verify we have all phases, because we have a superposition of the PVDF phase here, and other phase, here is the peaks related to the BT. The SEM, is also interesting because here with the SEM, you will study, because we have modified, of course, the composition. I mean here, the rate of BT. So that means BT we load, finally the PVDF with BT, and we have modified, the rate of BT from 7% to 30%. And what we observe on these different photos, that here in particular we have a zoom, for the 30%, and we observe we have some abnormal rate, for this rate, this loading rate. That means for us that 30% is the limit, because when you have abnormal rates, you modified the electrical properties, and it's not interesting. I will talk about that with the electrical characterization. Here you can see finally the electrical characterization. On the left, the direct constant. On the right, the lost engine. So here you have the first study, the first curves for the different loading rates. You have the pure PVDF here without BT, and after that we have the increased loading, 7%, 15%, and 30%. So finally we obtain, the highest value of the electric constant for 30%. For the losses, that was different. You can see different curves. And you have a difference, in behavior. And this here, when you make measurement, you have to focus because I have conducted, an additional study about the behavior of this, in particular with this behavior here. And what we can see here, in difference with that, here you don't have any relaxation at low frequency, but what you can see here is a relaxation. You have a domain of relaxation, and this relaxation is due to the agglomerates that you have in your composite. What kind of relaxation is it? It's a domain which is due to a Maxwell-Wagner effect, because you can have an accumulation of electrical charge into your agglomerates. So finally, that means that for us, this 30% of BT is the maximum loading we can use. But nevertheless, we were very satisfied with this result, because we have increased, very high, difference, the value of the direct constant, because for the pure PVDF we were at 12 for epsilon prime, and we increased up to 32. And the losses also were interesting. For the study of the phoretic cycle, we have also, an interest in that, because we have, of course, modified the remnant polarization and the shape, of the cycle. But here, as I said, we don't have an interest in the remnant polarization. We have an interest, in the calculation of the energy density. And here, in this plot, you have two evolutions. Here we have the discharge energy density, and on the right, on the other axis, you have, the stored energy density. So that means the blue curve, here is the stored energy, and the red is the discharge energy. And what is very interesting here is that we have, increased, the stored energy in function of the evolution of the rate of BT. So, also conclusion on this second part, if you want to realize some composite films, at first you have to master the dispersion of your ferroelectric particles into the polymer matrix. It's a very relevant point. After that, of course, we have made some demonstrations that is interesting to add some ceramic particles into the polymer matrix because we have increased the value of the dielectric constant. We have also modified the random polarization because we have an evolution from 1.3 microcoulomb per square centimeter for the PVDF to around 6 microcoulombs per square centimeter for the loaded Betty. And we have also an interesting value of the recoverable energy density, especially for this 30% of volume of BT. So the last part of my talk, it's a shorter part because I just want to present you because it's in my opinion. Yeah.
Yeah, you still have 10 minutes include the question and answer.
Yeah. Just I will go very fast about that because I just want to, because it's also interesting, I guess, for Indonesian researchers. As you know, Risa, I well know the situation in Indonesia, and I guess this is something which can be done, in Indonesia because here I'm gonna talk about ab initio calculation by using, the density functional theory.
Okay.
That means that you want to predict, the behavior and the properties of a material by using a software. So here the calculation method is we are made, by using, the FIN2K package, and this package, is based on the density functional theory. You have also finally an exchange correlation potential, and you use, some special approximation here, Peugeot and Zenoff, and modified Beck-Johnson approximation. What is important to say is that in these simulations, because primarily you use software, so this is simulation. In this simulation, you have to limit because it's impossible to study, for a high number, of cells, because of course the power of calculation should be, a function of the number of cells. Here it was we have studied 2 by 2 by 2 cubic perovskite supercell with 40 atoms, and for this calculation, we already needed a lot of time, and the more cells you have, the longer the calculation will occur. And here we have conducted a study, about the BSN structure doped with cobalt. So at first we have here, because we have studied with this kind of software, you can study a lot of properties for semiconductors. And I will only present here the electronic properties because it's interesting for, I repeat it, for prediction. So here I present, the band structure of our BSN03. I chose this material because it's interesting for solar cell application. And here in this electronic properties, you can see the energy band. And what we have seen, this is the simulation. If you used to study, the conduction bands, of semiconductor, you can see that at this point you have a difference, between finally what we call, the valence band maximum and the conduction band minimum. And here, this these maximums are not, at the same place. That means it's here and here. And that means that we have here that BSNO3, is an indirect bandgap semiconductor. With this simulation, you can also, of course, measure the energy gap. Here it was 2.62 electron volt. After that, we have doped our material with cobalt. We have doped the BSNO3 by cobalt with different rates, 4 rates, from 12.5% to 50%. And here, for the different graph here is for the first level, B, C, and D, for the different doping rate. And I put different red arrows, on the graphs to locate more easily for you, to show it. Here the maximum, and the minimum of the conduction band and valence band. That means here they are positioned, at the same place. And finally, what that means? That means that we have, by doping our BSN by cobalt, we obtain now a direct energy bandgap. That was for us very, very interesting, because we have transformed our material from an indirect to direct, bandgap. Yes, and finally, we have obtained a direct energy bandgap with the use of the zero dopant. And we obtained for the zero dopant BSNO3, a p-type, what we call a p-type degenerate semiconductor. And this is the evolution of the different value of the bandgap, okay, in function of the concentration of cobalt. And what you observe, we have obtained, and this is simulation results, okay, we have an important decrease of the bandgap. And of course, the lowest, bandgap value was obtained, for 40%, with 50% cobalt. And this lowest value, is very interesting, because, as you know, when you have an interest in solar cells, by comparison to the famous silicon, it's also more interesting to have, a low value for the bandgap. So, I just presented some result because we have done also calculation of course, with DFT, but I wanted to present it a little bit, because I guess this kind of tool can be used, by Indonesian researchers, and it's very important, very interesting, because it's a powerful tool, for the prediction of, in particular, electronic and optical properties for semiconductors, of course. So, merci pour votre attention. Thank you for your attention. Terima kasih atas perhatian Anda.
Okay, thank you, Prof. Didir, for inspiring presentations. Ladies and gentlemen, Prof. Didir talks 3 parts. Part 1 about ceramics, about ceramic, and then composite material, and finally density functional theory predicts electrical and optical properties of semiconductor. Okay, ladies and gentlemen, Bapak dan Ibu, any questions? We have about 5 minutes. It is limited times. Okay, the first one. Okay, Prof. Ari, please. Okay, Prof. Ari, yeah.
Thank you very much, Pak Risa. Hello?
Yeah, okay, please.
Professor Hidir, how are you?
Yes, Ari.
Yeah,
I'm
Nice to
very
meet
pleased to hear you.
Yeah, nice to meet you again. I've been seeing you for 2 years. Yeah, we met 2018 when we have what is lobster and crabs with
Yes,
Jovan. Okay, next time when you know the pandemic end, you can come to Indonesia again.
of course.
Okay, yeah. For my question regarding about the interesting your presentation, PVDF. Yeah, 30 years ago, I was working with PVDF for ultrasonic transducer
Yeah.
for medical application. The problem is the piezoelectric polymer PVDF, the electromechanical coupling constant is low compared with the ceramic one, say PZT, BT, etc.
Yes.
So can you tell me regarding about the electromechanical coupling constant of your ceramics and also for your composite between PVDF and ceramics? Yeah, as we know that the PVDF is it is founded by the researcher from Japan, Professor Kawai, if I'm right in thinking. It is right?
Yep.
Yep. Okay. Can you tell me about that one regarding about the electromechanical coupling constant, because you haven't shown the measurement, or maybe you are not interested for the piezoelectric properties. Thank you very much, Professor Didier.
Yeah, Ari, thank you very much for your question. Of course, we are talking at this time, if we are talking about electromechanical, properties, we are talking about piezoelectric behavior. In this way, you have two things. You can, of course, we can talk about the direct effect and also for the converse effect.
Yeah.
But here, in my study, I wasn't interested in these properties because, as I said it, for electrical energy storage, you don't have an interest in these piezoelectric properties.
Yep.
Because here our main goal was to increase at first the dielectric constant, and it was very interesting, by adding, in this composite, by adding some ceramic powder. But of course, as you've seen, we have also increased, the ferroelectric properties. But as we didn't have any interest in the piezoelectric effect, we didn't measure the piezoelectric properties. But I guess, of course, because I have also in France, I have some colleagues, who have studied, finally, also the effect of the addition of ceramic powder into the polymer matrix. It is in a current, a research project, and they have a special interest in flexible material dedicated to piezoelectric applications, and they also added some of course ceramic particles into polymer matrix. And they have also observed the increase of the piezoelectric properties in this way. So this is an interesting thing for all applications.
Yes, I think so. Because last time when I become a research assistant at CSIRO, Commonwealth Scientific Industrial Research Organization in Australia, I did a lot of publication for the this underwater hydrophone using PVDF.
Yeah.
Because for the characterization of ultrasonic transducer for medical purposes. But the problem is the electromechanical coupling constant is very high.
Yeah.
But the acoustic impedance is low. It's good. It's mean because it's close to the human tissue body acoustic impedance. But the electromechanical constant is very low compared with ceramic one. So that is why this is very interesting when you talk regarding about the composite material between PVDF and BT, barium titanium trioxide, is very, very interesting. So I would like, further have a look regarding about, the properties of piezoelectric material. Properties and also the electromechanical coupling constant and also the acoustic impedance in order for the medical application. Thank you very much, Professor Didier.
You're welcome. Thank you.
Okay, thank you, Prof. Ari, for your questions. But because limited times, the time is over. Thank you, Prof. Didier, for joining in this conference. I hope we can meet in the next years of the next Icopia 2022. Okay, Bapak dan Ibu, ladies and gentlemen, I'm sure you want to extend discussions, but yeah, unfortunately, the time is over. So in the second plenary sessions is enough. So the next agenda I will give to Master of Ceremony.
Professor Didier. Professor Didier.
Yeah.
It is possible you come here sometime next year for
yes,
the discussion.
As soon as possible. Maybe as you know, finally the situation in Europe now is good because we don't have a lot of cases of COVID, at this time. So finally, the situation is pretty good, here. So I hope the situation will evolve, in the same sense, in Indonesia. As soon as possible, of course, because if the situation is good, I guess I will be able to come in Indonesia, at the end of this year.
Okay, yeah, your friend will invite you, and we invite you as well, Just have a look regarding about the situation of COVID. Okay, thank you very much. Okay, gitu aja, Pak Risa.
Okay, yeah, I'm sorry, Prof. Ari, because the time is over. Okay, Safira, please.
Thank you, Dr. Risa Suryana, for being the moderator for the second plenary lecture session. Ladies and gentlemen, we are now at the end of the plenary lecture session. Next agenda will be the parallel session. The parallel session will begin at 1 p.m. and here the rules for participants. First, each presenter must be in the virtual room throughout the session. Second, one presentation is allocated 15 minutes, with 10 minutes for the presentation and 5 minutes for the question and answer session. Presenters have to close the presentation strictly within 10 minutes. Third, session chairs need to strictly control the start and closing time of each session. During your presentation, the session chair will give you notification via Zoom chat 2 times, indicating that your time allocation is coming to an end. First notification, 2 minutes presentation time remaining. Second notification, time is over. Finish your sentence and stop your presentation. Fourth, the question and answer session. Participants give questions through chat that will be read by chair, or directly unmute your microphone. But please ask the chair's permission first. Once again, we give many thanks to all of our wonderful speakers. We thank every committee member for the wonderful accommodation. I am, as Master of the Ceremony for this conference, will sign off. Thank you, and see you in the 11th International Conference on Physics and its Applications 2022.